Hello everyone, myself Dr. Badala Rajshekar, Associate Dean Sustainability and Assistant Professor Civil Engineering Department, SR University, India. And today's my topic is hydrologic cycle. So before going to the topic, I would like to give some introduction regarding hydrology. Hydrology is nothing but the study of water. See, hydrology. Logy means steady. Hydro means water, the study of water. So, hydrological cycle indicates here, hydrological cycle indicates the study of something it is giving continuous process. Cycle means something it is continuous. So, hydrological cycle means something it is continuous. So, what is that something means? Here we can see the movement, occurrence, movement and distribution. So hydrology studies means the occurrence, movement and distribution of water on earth. That means in a simplified way, if I want to give some kind of example, this we can take as a reference for our example, water cycle. Water cycle is also known as hydrological cycle. See, as we know that from clouds we are receiving precipitation. Precipitation is nothing but in terms of rainfall, snow. So once the precipitation here from clouds to it is reaching it down. That means on ground. So there will be some interceptional losses that we will discuss afterwards in a simplified way. There we can see some kind of clouds, and from there we are seeing some kind of precipitation. That means rainfall. After rainfall, we can see some amount of water will reach to groundwater. Obviously, after that some amount of water which is we can see on the streets and on the surface of the earth, we can see some water is running away. That is nothing but surface runoff. And here also you can see there is some kind of losses in terms of evaporation losses and evaporation loss as well as the precipitation loss. So losses in the sense we are losing water. Whatever the water we are getting from atmosphere in terms of from clouds in terms of precipitation, we are getting recharge in terms of groundwater and surface water runoff in terms of like overland flow, and losses also we can see. That means water is escaping from earth to again going back to atmosphere. That means going back to atmosphere means evaporation is nothing but the water which is lost with respect to water bodies. So water which is lost with respect to water, it may be ponds, it may be lakes, it may be ocean, or it may be something else which is having the water. And another one is nothing but transpiration. Transpiration in a simple sense, the water which is lost with respect to plants, that means leaves, that is called transpiration. So both are the losses. So now cumulatively we can tell that there is a kind of precipitation. Precipitation means rainfall or snow, but precipitation we got. And if you the runoff we are getting runoff. So runoff, and we are having recharge, groundwater recharge. And some losses we call it as evaporation and transpiration. So here we can see now, that means occurrence means rainfall. Movement means after rainfall some amount of water is reached to groundwater table and some amount of water is in terms of runoff. And distribution means maybe in terms of going back, like transpiration, evaporation, evapotranspiration. Now in a simplified way we can see it involves processes like evaporation means only with respect to water bodies. Condensation means at what particular point the water vapor is converted to droplets in atmosphere. And precipitation means maybe rainfall or runoff. And runoff means you people knows that precipitation means rainfall or snow, and runoff, these all components together we can see in on the earth surface. So now the process begins here. That means the first one, The water cycle is also known as hydrological cycle. The water cycle involves several key processes. As I mentioned, first one, we can expect a rainfall. After rainfall, we can see some kind of water is recharging in terms of infiltration, in terms of percolation, then in terms of groundwater recharge. Then we can see some amount of water is going away on particular surface. So that is runoff, and storage in terms of ponds, lake, reservoirs, and you can see condensation in terms of vapor, the water which is escaping from land to atmosphere in terms of mediators are evaporation and transpiration and evapotranspiration. These three, the water will escape in terms of water vapor. So this water vapor is converted to drops. That means drops in the sense water. So water vapor to water droplets, it is converted at a particular point, that is called condensation. And evaporation, as we know, transpiration, as I discussed just now. So now you can see scope of hydrology. So there is a lot of scope in hydrology. That means study of water. That means you can study with respect to surface hydrology. That means rivers, lakes, reservoirs, and in terms of groundwater hydrology, aquifers and subsurface flows, and in terms of watershed hydrology, analysis of watershed, catchment, basin. One thing I want to clarify that there is a river called river with respect to area, we call it as basin. Also we call it as catchment. Also we call it as watershed. So depending on size, that means, so depending on area, the names will be fluctuated. That means different names will be there: watershed, catchment, and basin. And environmental hydrology, that means interaction between water and ecosystems, also we can see in terms of the scope. Now coming to the point, okay, where these all things are where this all can be applied, like applications of hydrology. So for particularly we can see water resource management, and next one flood control, and next one irrigation systems. As we know, irrigation system we have to be more precise, and urban drainage, which is the most every time we will face lot of issues regarding urban drainage, and hydropower projects, as well as groundwater recharge, as well as environmental impact assessment. Not only this limited, there are many things which are related to applications of hydrology. Next, the next simple thing, actually, as I mentioned, see, this is what you are seeing on the left side, that is called watershed. So watershed is nothing but, here you can see some blue lines are there, some blue color lines. So this blue color lines indicates ridge line. That means here this may be watershed 1, this may be watershed 2. So here one watershed will be there, and here one watershed will be there. That means both, that means this ridge line means is nothing but highest elevation. That means you can treat it as a mountain. For example, you can see here there is a mountain. Okay, the water, whatever the water is there, it will come downward this side, and whatever water is there, this will come down this side. So this line acts as ridge line. That means this is one watershed and this is another watershed. That means in a simple way, higher elevation to lower elevation. So here, from here water will starts, and it will comes to up to here, and it will go reach to the outlet, and this particular point we call it as outlet. That means the entire water will reach here, whatever the rainfall is happening. Maybe the rainfall you can see here, or you can see here, whatever, everything will comes here, and we will measure in terms of meter cube per second. That is nothing but discharge. So divide here, this major line is river, and you can call it as small immediately joined one is called tributaries, and immediately another one joined is called sub tributaries. So main river, tributaries, sub tributaries. So connection, like we call it as in a terminology like first order, second order, third order streams. Now we can see the definition of drainage basins. As I mentioned, basin or catchment, like a basin or catchment or watershed, everything is same. Now we can see a drainage basin or a watershed is a geological area where all surface water converges to a single outlet through a network of rivers and tributaries. As I mentioned, this is a watershed and combination of subtributaries, tributaries and main river. They are the collectors. They will collect the water and they will bring at what one outlet location. That may be a ocean or something else. So that's what they are mentioning here clearly. Drainage basin is nothing but entire area with respect to network. And coming to another like in a three-dimensional view, if I want to show, as I mentioned, there will be an elevation and two watersheds are shared. One watershed will be coming this side, another watershed will be that side. So now you can see here, this is the elevation point. So now you can see higher elevation and to the lower elevation. Obviously water from higher to lower with respect to gravity, and you can see this is the main stream and this is a tributary. This is the main stream and this is the tributary, and this is a subtributaries. So if one more, if we have a chance, we can go subtributaries and we can go here subtributaries. So and confluence is nothing but meeting two rivers at one point. That means one river is coming this way and one river is coming this way. And drainage divide is nothing but both rivers. Is mouth of the river is also known as outlet, and main river channel, as I explained, tributary means main tributary, and if is having another one, that is a sub tributaries. So springs means we can see naturally water is coming out. Now we can see different types of drainage patterns. So different types of drainage patterns means one is dendritic drainage pattern. If someone is mentioning what is dendritic, this is the shape of the dendrites you can see. And radial means you can see this is a radial pattern, and trellis means this is a trellis, and rectangular means this is a rectangle, and irregular means this is a irregular. So mostly you can see this kind of patterns in many areas. That is dendritic river like patterns, drainage basin patterns. And coming to the characteristics of drainage basins, you can see there are a number of characteristics, but here I am making a limited things: land use, land cover, slope, and drainage density, and size, shape, relief, and soil. So I'll explain each and everything in step by step procedure, such that you people can remember. And why? That means everything, whatever the drainage basin is nothing but there is a river. So there is a river. So here in this river, we can see this as a outlet, that is discharge. So in this river, you can see multiple networks are there, but every river never behaves similarly, because every river basin is having different characteristics. That means land use, land cover. Maybe one river basin is having kind of forest area is more. So if forest area is more, infiltration will be more. Some watersheds may be having more with respect to urban areas. That means if a watershed is having more urban area, that defines that particular area is less in terms of infiltration and more in terms of runoff. In the same way, slope also will make you difference drainage density and size. What is the size, what is the shape, as well as relief, as well as the soil. Every soil cannot behave in a similar path, so each soil will behave differently. Now we can see an example I have taken from one journal reference. For example, there is a watershed, and there you can see in 1978, this is a scenario. Green color indicates natural forest, and you can see immediately in 2008, this green color area is dominated with respect to investment of coffee plantations. Okay, let it be. Then they made it a future prediction, and here you can see the areas which is having here drastically agriculture, and settlements. That means here itself you can understand the land which is in 1978, which is dominated by forest, but in 2008 it is completely dominated. That means replaced the forest area with respect to investment or coffee plantation and agriculture and settlements. But it was predicted that in 2025 the more agriculture and settlements will be replaced comparatively 1978 and 2008. That means this trend is increasing. That means here maybe the forest area is more, so infiltration capacity will be more, but here the infiltration is reduced. Here infiltration is more reduced, but it is encouraging for runoff. That means that's what as I mentioned, every watershed is not unique. Every watershed never gives in a similar path. So depending on each characteristics, it will behave differently. Now you can see one more thing, drainage density. Drainage is nothing but network. Here itself two examples you can see. Here left side figure is having high drainage network, and right side we can see low drainage network. That means what is the difference? What is drainage density? What is the difference? You people might know this thing. This is time versus discharge. That means at outlet we will measure meter cube per second. Here also there is a outlet, we will measure meter cube per second. That means discharge at outlet. Now you can clearly observe left side one is having high drainage density, right side is having low drainage density. Now you tell which one will give more kind of runoff. Here they are mentioning left side will give more runoff and right side will give less runoff. Yes, it is true. Why? Because I want to explain you in a both scenarios. Left side is dominated by urban area and right side is dominated by forest area, in a simple way to remember. That means the watershed which is completely dominated by urban area, that means there is no forest area to encourage infiltration. There is only construction will happen, so there most of the water will be encouraged to run off. That's what you can see. The first left side one is encouraging peak discharge, and second one is completely forest area. That's what the drainage network will be less, so the runoff will be less. So if more drainage density indicates, in a simple way, urban area you can remember, and flood will be more. If less drainage density indicates forest area, runoff will be less. And there are many things, classifications in worldwide, but I want to give you simple things. Depending on soil types, alluvial soil, black soil, red soil, mountainous soil, depending on these soils also, the watershed will behave differently. That means here it is not only every soil, like as I mentioned, every watershed is not unique in that characteristics. First one, all watersheds are not having in a similar path. Similar path means in terms of land use, land cover, in terms of drainage density, in terms of soil. And next one you can see, the another one is key important role is size and shape. Here you can see this part is narrow, that's what here we got peak, but here it is broad, so we didn't get peak. And here you see this part is broad, so we didn't get peak, but this part is narrow, so we got peak. Here two are there, so two peaks we will get. So depending on not only on land use, land cover, not only on soil, not only on drainage density, but also size and shape also matters. So next one, coming to the point, slope. So slope also plays the crucial role. As you people knows that this is a very basic thing. Depending on the slope, the drainage basins will trigger runoff. And hypsometric curves means, in a simple sense, it will measure soil erosion percentage. That means till now how much percentage of soil is eroded in a particular basin. Then accordingly they will do some kind of remedies. So that is what hypsometric curves. And next topic we can see forms of precipitation. So forms means there are many different kinds of forms classified worldwide. But if I want to take, there will be simple forms: rainfall, snow, as we know from our childhood. But these are the little technical words: drizzle, glaze, sheet, hail. So these are the little technical words where we are going to use in the upcoming lectures. That means rainfall, everyone knows that we can see in terms of monsoon. But rainfall means depending on the see in a common way, everyone, as a technically, as I mentioned, in water cycle there will be a precipitation, and there will be a groundwater recharge, and there will be a runoff, and there will be a transpiration, evaporation, and there will be a condensation. So this is the cycle what I have explained before coming to the my main lectures. Now we are going into the first one called precipitation, because without understanding these all things you cannot able to do any kind of management strategies for any watershed. As I mentioned, watershed and characteristics of watershed. What are the characteristics of watershed? LULC, land use land cover, soil, slope, and soil, slope, drainage density. So this and more, and hypsometric curves, as well as relief, that means elevation, this all comes under the drainage basin. That means you should know the dry. If you want to know clearly about a basin, so you need to learn what is there in the physical form. That means what is physically available: forest area, what is the forest area, what is the agriculture area, what is the urban area, what is the barren land. Everything you have to know. In the similar way, what is the soil, what is the slope, what is the drainage density, what is the hypsometric, what is the relief. In the same way, if you want to tackle watershed in a good way, like a management perspective, you should know other techniques, terminologies like, and effects like precipitation. You should know what is precipitation and how is going to affect. And you should know runoff, you should know groundwater, and you should know transpiration, evaporation, and another one is evapotranspiration and condensation. If you know all this full-fledgedly, then you can able to understand what is watershed and how you can do some kind of measurements. So now coming to the point, rainfall. So precipitation having major one, because without precipitation there is no so-called, like we can tell, there is no life. That means if there is no rainfall, there is no water. If there is no water, there is no life. So we have to understand, we have given the classification with respect to the rainfall. Rainfall means, in terms of precipitation, raindrops. So drops of water larger than 0.5 mm in diameter. It is the principal form in India with intense classified. That means greater than, like larger than 0.5. Again, it is classified as, if you are telling light rainfall, it is 1 to 2.5 mm per hour. If it is moderate, 2.5 to 7.5 mm. If it is heavy, 7.5 mm per hour. So it was broadly classified. Rainfall means, in a simple way, if you want to remember, which is having larger than 0.5 mm in terms of size. Next, snow. Snow, as you people knows, and there is no need to explain much about snow and rain, or you can identify easily when they are appearing physically. So Himalayan regions. And coming to the drizzle, here you people need to understand, drizzle is nothing but with the size which is having less than 0.5 mm rainfall. Means that you can take the size means dia of the drop. Next, glaze. Glaze is nothing but if I want to give something, freezing rain forming a coat of ice. That means, what do you mean? Freezing rain form a coat of ice. That means something, you can, people knows that refrigerator, in deep refrigerator we can see some kind of ice is formed. In a similar way, if you want to understand, I have given a image glaze. You can see this is called glaze. Okay, another one is called sleet. That is, the range is between 1 to 5 mm. And another one is hail, that is greater than 8 mm in terms of diameter. So these are the broadly classified in terms of precipitation. And types of precipitation, some few types are there. Convective precipitation. In that convective precipitation, you can see this occurs due to heating of ground and temperature difference between moist air and its surrounding. That means, you can see here, there is a warm air and there is a cool air. That means, here you can see it is a temperature difference between moist air and its surrounding. Example, summer rains, high intensity rains occurs for a short period. And next type is called orographic precipitation. Orographic precipitation is very, very important, and you people need to remember. See, at certain extent, this thing, rain, that clouds will travel only certain distance up, and more than that it cannot go. That means, here you can see it is caused by topographic barriers. In India, you can see southwest monsoons starts from Kerala, Karnataka, and it will go. But you can see this is like Tamil Nadu area. That means, this is Kerala and this is Tamil Nadu, which is obstructing Western Ghats. So here this is called orographic precipitation. Here the rain will be more, and here there won't be any kind of rain. That is called leeward side. In a technically speaking, we call it as leeward side. This is windward side. And you can see another two kinds of types. Frontal precipitation. It is an interface between two distinct air masses, warm air, cold air. And cyclonic precipitation is nothing but it occurs due to difference between ground and water bodies. So now the characteristics of precipitation in India, if I want to explain. So as I mentioned, there will be two kinds of monsoons, southwest monsoons and northeast monsoons. Southwest monsoons will be more like June to September. And coming to the thing, if you want to know more, means 75% of annual. And post monsoon is transition, that is October to November, moderate rainfall, that is in state called Tamil Nadu. And coming to the winter season, December to February, scanty rainfall and mainly occurs in Jammu and Kashmir. And another one, pre-monsoon summer, that is localized storms and scattered rainfalls. If you want to need more explanation, here I can give you in a image way. See, as I mentioned, southwest monsoons that will comes from this side, and you can see here, you can see Western Ghats. That's what first it will touch Kerala, next Karnataka, Andhra, Telangana, Maharashtra, and it will go up to the here. Next, after finishing this thing, next one is northwest monsoons. It will be majorly focused in Tamil Nadu. So now you can see the measurements of precipitations. So here you people need to remember, precipitation is measured as a vertical depth of water that would accumulate over a level ground if precipitation is retained where it fell. And next one, it is expressed only in mm or centimeters. It's not in meters. Please remember it. And it's in technically we will call it as rain gauges, also known as ombrometers, fluviometers, hydrometers. So there will be two different kinds of gauges, rain gauges. Rain gauges which will measure the rainfall. So there will be two rain gauges, that is called non-recording and recording. And in rod recording, we can see Siemens and IST. And another kind of things, tipping bucket, weighing bucket, siphon and radar. And this is one example of Siemens rain gauge. So density of rain gauge networks were broadly classified into three categories. So you can see here, that means if it is a flat one, if area is plain and flat, that means if it is area is 530 kilometers square, one rain gauge is sufficient. If elevation is greater than 300 meters, then one rain gauge is sufficient for every 260 to 390 kilometers square. If it is mountainous and hilly areas where we have to focus more precisely in terms of measuring the rainfall data, where every 130 kilometers square we have to go with one rain gauge. Okay. Optimum number of rain gauges. So we'll see some kind of problems regarding optimum number of rain gauges. Before that, we will see some kind of procedure. What is the procedure involved in finding optimum number of rain gauges? So next one. So now here you can see the step-by-step things for calculating the optimum number of. Here this is our ultimate agenda. Optimum number of rain gauges is nothing but it is denoted by n. Now you can see first we understood what is precipitation and we came to solve some kind of problems because precipitation means rain gauges. So optimum number of rain gauges we are going to calculate, that is called n. As I mentioned earlier slide, there are three different kinds of locations. One is flat, one is elevation more than 1000 meters and one is hilly terrain. For these three areas we are maintaining one rain gauge at different places, like flat, like a different area. That means area is with respect to kilometer square. Now find mean of rainfall. That means just we have to find p bar, number of rainfalls divided by m, that means existing. Next, finding the standard deviation sigma. Sigma is equal to under root summation pi minus p bar. P bar means here we are finding the p bar which is utilized here. Next, coefficient of variation CV is nothing but from sigma we will get standard deviation, that is standard deviation, and p bar we will, by using this both sigma and p bar, we will get coefficient of variation. From coefficient of variation we can use n is equal to optimum number of rain gauges CV by E. E is nothing but the percentage of error. That means percentage of accuracy is nothing but 100 minus error. If you remove error, that is called accuracy. Now we can see the first problem. Quickly we will see. A catchment has three rain gauges. A catchment is having three rain gauges. That means given data m is equal to 3. A catchment is having three rain gauges that is existing. In a year, the annual rainfall recorded by the gauges are follows. That means P1 equal to 80, P2 equal to 100 and P3 equal to 180. So 3 they have given. Now our agenda is to find P bar from these 3. That means P bar is nothing but P1 plus P2 plus P3, that is 80 plus 100 plus 180 by, it's not average, it is M. As per our previous thing, here you can see first step. What is the first step? P1 plus P2 plus so on by M. That is how many they have given? 80 plus 100 plus 180 by M is nothing but 3. M is nothing but 3. Now we will get P bar. Now next we have to find sigma. What is sigma? Sigma is equal to under root of Pi minus P bar whole square by M minus N. We'll get sigma. Next we have to find coefficient of variation. Coefficient of variation is equal to 100 sigma by P bar. That is what, as I mentioned. Next, after that, he need an optimum number of rain gauges. Optimum number of rain gauges is nothing but CV by E whole square. Now you can see what is E. E is equal to 9 percentage. Sometimes they will give 91 percentage accuracy. It defines there is a error of 9 percentage. So accordingly you have to take and you have to be precise in terms of understanding the question. Now you can see the solution. As I mentioned, E is equal to 9 and M is equal to 3. So in question itself they are given 80 plus 100 plus 180 by 3 is nothing but 120, and standard deviation formula sigma is equal to root of under root of summation xi is also known as pi minus p bar whole square by m minus 1 sigma. So what is pi? Initial pi? Initial pi is 80, next p2 is 100, next p3 is 180. What is x bar is also equal to p bar. What is p bar? 120. What is p bar? 120. What is p bar? 120. As per our thing, pi minus p bar whole square. We done whole square for everything. And m minus 1. M is equal to 3 existing rain gauges which is having the rainfall data 80, 100, 180. And finally we will get sigma. Next, coefficient of variation. Coefficient of variation is equal to CV equal to 100 into sigma by p bar. So P bar also known as X bar, as I mentioned earlier. So now you can just substitute P bar. What is P bar? 120. What is sigma? 52.9. So you got 44.083 percentage. Next, N is equal to final number of optimum rain gauges. N is equal to CV coefficient of variation by E into whole square. What is CV? 44.083 percentage by E, error we know from the beginning we got 9 percentage. So definitely the optimum number of rain gauges how many? 24. So we got finally the value N equal to 24 is a final answer. So now we can see one more problem, similar problem. There are 4 rain gauges in a catchment. Okay, very good. That means immediately we have to write what number? So if you are watching this video, please stop this thing and try to solve, because one problem already I have discussed. So m is equal to 4. You just try to solve, then see. Next, what is the E value? Equal to 90 percentage accuracy. As I mentioned previously, if accuracy is 90 percentage means a percentage of accuracy is equal to 100 minus percentage of accuracy equal to 100 minus E. So what is the E? E equal to 100 minus percentage of accuracy. So E equal to 100 minus 90. So E equal to 10 percentage error. So error is nothing but 10 percentage. So what is P1, P2, P3, P4? So P1 equal to 3, P2 equal to 5, P3 equal to 6, P4 equal to 8. So from this we can find what we can find? P bar. P bar equal to P1 plus P2 plus P3 plus P4, 3 plus 5 plus 6, sorry, P bar equal to 3 plus 5 plus 6 plus 8 by existing rain gauges 4. So P bar equal to, what is the value P bar? 5.5 centimeters. In a similar way you can solve sigma. Sigma is nothing but, as I mentioned, under root summation pi minus p bar whole square by m minus 1. What is m? 4. We know that. And pi is nothing but 3 p1 plus p2 plus p3 p4. What is sigma? P bar. Just substitute it, you will get answer. So sigma is around 2.08. Now we got everything. Now another one is another one we have to do a small kind of thing, coefficient of variation. So sigma is equal, cv is equal to 100 into sigma by p bar. So we know sigma 2.08, we know p bar. So definitely we'll get cv 37.81 percentage. Now finally number of rain gauges. So number of gauges cv by e whole square. So we just substitute it, you will get 15. So now this is not what they need. So this is not a solution what they need. So they need the solution. You can see from previous problem, this problem, they are asking one additional line. Also recommended number of additional rain gauges. So number of additional rain gauges means I have skipped one part. Initially, you can see there are two conditions. Condition 1, condition 2. If n less than m, that means n means n means you can see here optimum number of rain gauges, m means existing rain gauges. If optimum number of rain gauges are less and existing rain gauges are more, no need, there will be sufficient gauges. If n is greater and m is less, then you have to go for n minus 1. That means I will show you here. What is the value of n? Just look at here. What is the value of n? N is equal to 15. What is the m? M is equal to 4. Now you tell which is greater. N greater than m. That means 15 always greater than 4. Now simply you can do n minus m. What is n? 15 minus 4. That is equal to, you can recommend 11. So recommended number of rain gauges are 11. You can see here a simple classic clarify. Again, once again I want to clarify. So we got sigma, we got p bar, also known as x bar, we got x bar, and we got cv, and we got n is equal to cv by e whole square. Already, as I mentioned, percentage of accuracy is also equal to 100 minus error. So we got 15. So number of additional rain gauges, n minus m. As I mentioned, n is equal to 15, m is equal to existing 4. Now you can see n greater than m, obviously 15 greater than 4, obviously. So now 15 minus 4 is our standard formula where we can make this thing. Okay, got it? Shall we try one more problem? One more similar problem, but just they have given more number of gauges. That's only the difference you can see here. The one thing is that here how many gauges? A, B, C, D, E, F. That means M is equal to 6. That is the only way they have given more. And immediately you have to note down what is the error, 10%. Okay, done. What is the P bar? P bar is nothing but P1 plus P2 plus P3 plus P4 plus P5 plus P6 by 6. Then you will get here 118.6. What is the sigma? Sigma is nothing but root of summation into pi minus p bar whole square by m minus 1. That is 6 minus 1. So sigma, what is the sigma value? Please pause the video and try to solve it. Then only you people can understand what is going here. Simply listening, you won't get anything. So CV is equal to, so what is the CV? 100 into sigma by p bar. So now you can tell what is the value of sigma? 35.03. What is the value of p bar? 118.86. Then what is the value of CV? 29.53. Next, optimum number of rain gauges. What is the optimum number of rain gauges? N is equal to CV by E whole square. What is CV? 29.53. What is E error? 10. So n is equal to 9. So it will be 8.72, but try to take every time 9. Now you can see everything will be visible. M we know 6, P bar 118, sigma we know 35, error this one. So coefficient of variation 100 into sigma by P bar. Next n is equal to CV by E the whole square. That is equal to, every time you take, if it is 8.7 or 8.1 also try to take it 9, around 9. Now if you want to measure additional rain gauges, so here n equal to 9, m equal to 6. So n greater than m. That means 9 greater than 6. That means 9 minus 6 is equal to 3. So we need, hence 3 more additional stations are required for this particular area. Now finally we will see one more problem in optimum number of rain gauges. A catchment has 5 rain gauge stations. Very good. So what is the value? M is equal to 5. Very good. 6% error. Okay, very good. 6% of the error in estimation of mean rainfall and coefficient of variation of rainfall existing stations is CV. That means CV is equal to 20. Determine n. So how to solve this thing? Please pause the video and try to solve it, then you people can able to understand. Okay. So now they were not mentioned what is P1, what is P2, what is P3. If we come to know, we might solve P bar, and we have solved one more thing is called sigma, and then we will come with sigma CV is equal to 100 into sigma by P bar. But they were not given these all things, they were given directly CV. So we can solve directly. N is equal to CV by E whole square. So what is CV? 20. What is N? Sorry, what is E? 6. That is nothing but 20 by 6 whole square equal to 11.11. That also equal to 12. So now we got 12. So number of stations additionally. So N is equal to 12. M is equal to 5. So N greater than M. That is 12 is greater than 5. That is simply you have to go just minus. That is N minus M. That is equal to 12 minus 7. 7 is the final answer what they are expecting. So additional number of gauges 7. So you can see here the final answer. So number of rain gauges. Number of rain gauges 5. Error 6. CV. So n is equal to, as I mentioned, n is equal to CV by E whole square. So n is equal to CV by E whole square, that is equal to 11. So take it as I mentioned, if you are getting the point 11.1 also you take it as 12, 11.6 also you take it as 12. Don't neglect it, because even 0.1 also will may fluctuate more. So just take it as 12. So the optimum number of gauges is 12. So as I mentioned, n minus m, because obviously it is n greater than m, so you will get 7. That is what I have solved. So try to solve before I am solving, when I discuss it after my first problem. So next topic, optimum number of rain gauges, we want to focus on estimation of missing data. So now estimation of missing data. Before using the rainfall data in hydrological analysis, the data is verified with the following conditions. First, you people need to remember continuity, consistency. Both are looks like similar, but they are not similar. Continuity is nothing but the data should be continuous without any broken information. That means each it should not have any kind of missing data. Consistency means data should be truly representative of the region. That means whatever the values we got, that should be true. That means we should not encourage any kind of false data. For example, if it is 1000 mm of rainfall, instead of 1000, if someone has noted down as 10 rainfall in particular monsoon, so that is like it is not up to the mark. So it should be truly representative of the region. Consistency is major important. So sometimes a rainfall amount of certain rain gauge station for a certain days may be missing due to the absence of some observer or instrumental failure. As I mentioned, because it is like in Indian standard, like everyone every day we will take daily data. So maybe if instrument is failing, it won't be continuous, and some observer absence also it won't be continuous. In such cases, it might be needed to estimate the missing rainfall data by approximating the value from the data of the nearby rain gauge stations. That means a set of data is here from 1990 to 2020. So in particular year 1999, in particular year the rainfall is missed. That means how we have to tackle it, because maybe the instrumental failure, or maybe some absence of the persons, or maybe because of the war or some other unavoidable circumstances it may happen. So how to adjust it? That means how to make sure that this missing data we are doing, we want to do some kind of research. So now there are two kinds of things: simple mean method and normal ratio method. In terms of simple mean method, you can see P1 plus P1 means that particular rainfall 1, rainfall 2, so on by M. And this one is normal ratio method. Now you people cannot understand, so we'll solve one problem in both scenarios, then you people will understand easily. So before that, these are the just terminologies: P1, P2, what is N1, N2. P1, P2 means normal like rainfall, and N1, N2 means here itself N defines itself normal annual rainfall. So I'll explain, don't worry, we'll have some kind of discussion such that we can solve this problem in a quick time. So now here the normal annual rainfall, A, B, C, basin A, basin like in a basin A, B, C, they have given. In sorry, in the year 1975, that means first one, normal annual rainfall means assume last 30 years of data or last 50 years of data. Assume that is 170, 180, 165, and in particular year 1975 station B data is missing. That means assume from 1950 to 2000, 50 years of data they have continuous data, average annual rainfall, that is 170, 180, 165. Now they need in particular 1975, there they have missed the data in terms of B. Here 153A, and there is no data, and 145. Okay, now we have to know what is the data in particular year 1975 with respect to B. So this is A, this is B, this is C. So now you have to target this data, that is in 1975 B data. For that, so you have to take corresponding 180 and just increase 10 percentage and decrease 10 percentage. Increase 10 percentage, decrease 10 percentage of value of particular 180. Because why 180? Because it is average of 50 years. So we need only 1 year data. So now increase 180. What is the value? If you increase 180 into 10 percentage, that is 198. If you decrease 10 percentage means 162. Now you check 162 to 198 whether this range is matching with 170, 180, 165, which is having 50 years of rainfall data. Yes, 162 to 198, 170 value is coming. 162 to 198, 180 value is coming. 162 to 198, 165 is coming. Whenever if you are having this kind of values, then simply you take it as 153 plus 145 by 2. Then you will get 149 centimeters. That is what here we can explain here. Here you can see the first method, simple mean method. You have to take that 180 centimeters. There you have taken plus 10 centi% minus 10%, that is 198, 162. Here you have taken the range 162 to 198, whether it is satisfying not. If satisfying, just a plus c by 2 you give, then p of b will be solved. For example, if the 10 percentage is not satisfying, then we will see one more problem. So this is also similar kind of problem you can solve by your own way. Here they have given normal annual rainfall. Normal annual rainfall means 60, 75, 80, 100. Now corresponding in 1990, you can see 90, 60, this is 75, and there is no data, and 70. Now just simply write it down. 80, the corresponding of this thing is 80 plus or minus 10. So if you do plus 10, it is 88. If you do minus 10, it is 72. Now you see 77 to 88, whether this all are matching or not. You just check this thing. This thing means this thing. See, obviously the last one is 100, which is greater than this range. So it is not satisfying simple mean method. Now we have to focus normal ratio method. In normal ratio method, just try to remember now. In normal ratio method, you can see what is the lagging one. This is A, this is B, this is D, but there is no C. What is the corresponding value of C? This one. So 80 by what is the actual existing one? A, B, D. That means 3. Now next into what is the value of 1990? That is 90. 90 by what is the corresponding one? 60. 60 plus next one 60 by 75 plus next one 70 by 100. If you have given in this way, then you will get rainfall with respect to C station is 80 centimeters. You can check rainfall with respect to C is 80 centimeters. So we have seen two kinds of methods, that is simple mean method and another one is normal ratio method. So how to solve the problems? Now one more example, you can stop it and you can solve this kind of problems for your like it's kind of a homework, and you will get this kind of thing. This is also comes under normal ratio, like a normal ratio method. As I mentioned, there are two things, simple mean method and normal ratio method. So this you can see normal ratio method. And next one is also same kind of problem. This one you can see another one problem. Please note it down. I will pause for some time. The normal annual rainfall at station A, B, C, D in a basin are 26.2, 35, 28.7 and 30.2 centimeters respectively. In the year 1985, the station A was inoperative and the station B, C, D recorded annual precipitations of 14.9, 4.9, 13.1 centimeters respectively. The estimate the rainfall at station A, which is missing in the year 1985. Okay, just make sure that answer finally answer is 9.2 centimeters. And one more problem, the normal annual rainfall at stations A, B, C and D in a basin are 75, 84, 70 and 90 centimeters respectively. In the year 1990, the station D was inoperative and the stations A, B and C recorded annually precipitations of 8.5, 6.7, 9 centimeters respectively. Estimate the rainfall at station D. So now you can take this as a one good challenging question. So now we have to find D. So hopefully this will also comes normal ratio method only. Please try to see this thing and answer should be 9.65. So next one is water budget equation. So water budget equation means in a simple sense there is a inflow and there is a outflow. Inflow is nothing but what is the inflow? Precipitation. What is the outflow? Runoff. Then percentage of change. That means storage. Storage means ponds, lakes, reservoirs. There is a kind of rainfall. There is a precipitation happen. After precipitation, we can see some kind of losses: evaporation, transpiration, evapotranspiration, and we can see some kind of runoff, and we can see some kind of groundwater recharge, and we can see some storage in terms of ponds, lakes, and reservoirs, and this entire thing will be happened in terms of basin. So now water budget is equation in a simple definition: inflow minus outflow equal to change in the storage. That is what is the inflow? Rainfall. What is the outflow? Runoff. What is the change happened in particularly watershed? So that will comes to the scenario. And this hopefully you can understand what is this, and we will continue in the next topics. Like next topic is rainfall losses. So rainfall losses is nothing but there are different kinds: interception loss, transpiration loss, evaporation loss, evapotranspiration loss, and infiltration losses. Now one by one we will see. So now the next topic, water budget equation, as I mentioned earlier. So in a simple sense, again I want to revise it because next step is very crucial. So inflow minus outflow equal to change in the storage. That means inflow is nothing but, in a simple words we can tell, precipitation, and outflow is runoff, and the change in storage means with respect to the losses like evaporation, transpiration, and evapotranspiration. These all things comes under losses. And we can see some kind of recharge, that is groundwater recharge. So after all the things, in a simple way, water budget equation you can remember in terms of inflow minus outflow equal to storage. Now coming to the things, rainfall losses, as I mentioned previous slides, interceptional loss, transpiration, and evapotranspiration, evaporation, transpiration, and infiltration. So now we will see, we'll discuss one by one what are the losses, how it happened, what are the factors affecting for these losses, and how to control it. If possible, we can see the measurements and anything else we can see. The first one you can see here, interceptional loss. So this is one kind of loss. That means in a simple words we can understand something is intercepting before reaching its target. So what is that? So reaching the target is defined. That means, for example, this is the ground level and something need to be reached at this location. That something is nothing but rainfall. Rainfall in terms of drops. So it will reach to the ground. So that is what expected from clouds. From clouds, rainfall, then it will reach to the ground. That means before here something is getting abstracted, that is interception. So you can see here clearly rainfall which is intercepted by tall objects lying above the ground. That means in between you can see from surface rainfall to here, some tall objects as we discussed, that is called it may be trees, it may be buildings, and so on. So before reaching its target, it is something is intercepting is nothing but trees and buildings. So rain without being collected on the ground, clearly in second line, as I mentioned in a simplified way, you can understand. So rain without being collected on the ground evaporates back. This is most important. That means rain will come and it will be stopped in between. That means the in between the thing is nothing but trees. That means leaves. It will stop it and it will make it go it back to, like in terms of evaporation to space from such objectives is known as interceptional losses. Now, as we mentioned, usually we have to take precipitation as a terminology. But here precipitation is having rainfall, snow, sleet, hail, and different kinds of names we have seen in the forms of precipitation. So okay, rainfall we have seen, we know the drop. What about the snow? Intercepted snow does not result in any notable amount of evaporation. Yes, obviously, whatever the rain is happening, immediately we can see some kind of evaporation. But when it comes to the snow, it is reverse. Why? Because immediate effect never happens. So after winter, you can see some kind of temperature increases. So slowly snow will get melted. So there you can see some kind of evaporation happens. That means, and here in the continuation you can see most of the snow falls off the trees by winds or melts. Melt means after increasing the temperature. That means after winter season we can see there will be due to heat the water starts evaporating, and while winter also we can see the kind of wind, it will be evaporated. So now we can see different factors which are influencing interceptional losses. So particularly for interception, so meteorological factors we can not up to the limit, so we can, there are many things are there. So meteorological factors means first rainfall intensity, rainfall duration, how much intensity the rainfall and how much duration it will take, and what is the evaporation rate at that particular area or the particular the watershed is very important to know before going into the things. Now another one is vegetative factor. So vegetative factors means it depends on canopy density, it depends on plant species and growth stage. That means what is the stage of that particular plant or a tree and how much capacity it can hold, or it can evaporate it back, or whether it is able to hold or it is able to transfer to the ground. So depending on different types of plants and their stage growth, you can decide. And there will be a few more several factors which can influence the losses. The first one is surface texture, and next one is slope and storage capacity of that particular interceptional losses, and these two also will play a crucial role in terms of wind speed, in terms of temperature and soil moisture. So wind speed means depending on the wind speed, it will disturb the capacity of sending back the water. That means through evaporation. So soil moisture also plays a crucial role. So next one, another loss in losses, there will be another kind is called transpiration. So transpiration, in a simple words, you can remember there is a tree and you can see some kind of leaves. So water is escaped through leaves. In a simple words, it's called transpiration. See, transpiration stands for tree. For your remembrance, see, tree means T. Transpiration means T. So remember in this way, and you can remember one more thing. Transpiration only happens with respect to trees. not with respect to water bodies like ponds, lakes, or any kind of things. So now we can see the basic definition. Transpiration is a process by which water exists living plants through the stomatal opening. I will discuss this thing to the stomatal opening in the leaves and diffuses into the atmosphere as vapor. Now, what is water vapor? Water vapor is nothing but it is in gaseous stage of water. So, water vapor from a plant leaf that passes through the stomato is called transpiration. So, in a simple words, for you people, for example, here you can see there is a image leaf. So water will be transferred from bottom, from the soil moisture to the branch and from roots, branch and stems, and finally it will reach to the leaf. And in your leaf you can see many small openings will be there. Many small microscopic opening will be there. That is nothing but from that water will go away, like how a humans will get sweat. So human body will get sweat. So in the like a same way they will have many openings of gaps will be there, pores. From these pores the water will escape to the atmosphere in terms of a water vapor. So these pores are nothing but stomatal openings. So transpiration will happen with respect to the stomatal. Now we can see some kind of important things regarding this transpiration. So transpiration is plant evaporation. As I mentioned clearly, T stands for transpiration and tree means T, transpiration means T. So plants. So transpiration only happens at daytime. So this is very important thing to remember. Evaporation from bodies like water bodies like ponds, lakes and oceans, it will happen with respect to 24/7. But transpiration happens only at daytime. So this is the most important thing. And transpiration is measured by a device is known as phytometer. This is also very good important bit where you can remember. So phytometer we can see, and daytime only it is measured. So evaporation only with respect to, in next topic we can see evaporation is with respect to, this is evaporation. Don't get confused with respect to the evaporation and transpiration, because evaporation is with respect to ponds, lakes and oceans, and transpiration with respect to trees, that means plants. Only it will happen daytime because of photosynthesis. Now we can see some kind of factors which will affect the transpiration. As I mentioned previously, some kind of factors which are influencing interceptional losses in the same way, but here the most of the factors will be similar affecting, but some specific factors are required for individually interceptional losses, transpiration, evaporation, evapotranspiration. Now you can see in terms of transpiration, as I mentioned, there will be small kinds of pores, like openings will be there for plants, such that from there the water is coming out. So number of stomatas are important, and leaf surface also important, leaf orientation also important, and plant type also important. So this all belongs to particular transpiration affecting the factors: number of stomata, leaf surface area, leaf orientation and plant type. And coming to the thing, another one, humidity, temperature, wind speed. These are mostly commonly depending on the area of the particular area, like watersheds. It may be not like it may be big watershed or it may be a small watershed, but depending on the climatic and meteorological factors, it will be having some effects. And light intensity also, because transpiration happens only at daytime. So light intensity also obviously it will affect the transpiration. And soil water availability, because if there is a soil water availability, only the plant growth will be there. So next, so rainfall losses, you can see interception loss we covered, and transpiration we covered. Transpiration means trees, interception means buildings or trees which is objecting before coming to the surface. And another one you can see evaporation. So as I mentioned earlier, many times evaporation is nothing but the water on the surface. That means it may be ponds, it may be lakes, or it may be oceans. So evaporation is a process by which water changes its state from liquid to vapor. Obviously, there is a liquid called ponds, lakes, or oceans. From that, it is going to convert to vapor. That is, vapor means in terms of gases, and it will escape to the atmosphere and it will go to the condensation. After condensation process, again precipitation. After precipitation, you can see some kind of runoff, some kind of groundwater recharge. After that, you can see transpiration, evaporation, evapotranspiration losses. Again, you can see back water vapor, and again water vapor will goes to condensation. That means atmosphere for clouds. See, this is a continuous process. That's what we have to encourage. Ponds, lakes, oceans, trees, and a forest, and everything we have to encourage the cycle, hydrological cycle. So we should not disturb any kind of the element in this. So next one, so we will see some kind of direct and indirect effects which we can see here. Directly related things are temperature in summer. That means temperature particularly in summer will affect more, and wind speed and solar radiation also will affect the evaporation and surface area of the body of a reservoir, pond, or lake. And see, this word you can remember. See, in summer evaporation more for shallow water bodies and less for deep water bodies. That means in a simple way, if I want to give a simple way, there will be more evaporation on ponds and lakes when compared to ocean. That's what, if there is a deep water bodies like ocean, there will be less evaporation, and there will be shallow, it will be more. And again, it will be further classified as quality of water. If quality of water is good, evaporation rate is more. So here whereas winter evaporation is less for shallow water bodies and none for deep water bodies. So it has compared both summer as well as winter for evaporation. That's what here clearly in the first point it has been mentioned that temperature in summer it is more, and quality as I discussed just now. So depending on the quality, the evaporation rate will be increases or decreases. So depending on the things. So next, as I mentioned, ocean depth. If depth of the water body is more, so it will be indirectly proportional. That means it is not going to contribute more evaporation, and that is depth also will plays a crucial role, as well as the humidity. And we can see some other factors which are doesn't comes under direct or indirect, but we can take it as a in terms of long-term effects. Like you can see some kind of human activities, for example, some kind of change in the forest area to urban area, or build or kind of agriculture or kind of other purposes, it may be affected. And the seasonal variations also will be affected, and vegetation cover, as well as salinities. That means it may be slow or high. So geographical location, as I mentioned, depending on the geographical location, everything will be changed. So desert, best example, desert you can see. And what are the methods to control it? So as I clearly mentioned the starting of the lecture, so some methods we have to focus. So methods means floating covers. So in reservoir you can see, nowadays you can see floating covers like plastic balls they are placing to reduce the evaporation rate. And some canals, for example, there is a canal, so water will flow, but this entire above part no one is using for other purpose. So we can make solar panels on above. That means solar panels over reservoir or canals, which we can utilize the space, as well as we can generate the solar power, and we can reduce the evaporation. And floating vegetation islands, this was also there in some places. And this all needs to be better reservoir planning in terms of wind break. That means planting around reservoir, planting trees around reservoir to reduce the wind speed. Obviously wind speed also will affect the, as I mentioned, factors, it will affect the evaporation. So if we are planting more plants around the reservoir to reduce the wind speed, and these all things can be controlled with respect to real-time monitoring. Obviously nowadays everything is depending on satellite data and artificial intelligence techniques. So we should know to know how to monitor that particular areas. That means for a particular region, if there is an issue regarding more evaporation or a less evaporation, it should be monitored regularly. So regularly we cannot go to the field and we cannot do the experiment. So we have to depend on satellite data. So that is the best way where we can get more outcome. So real time monitoring means satellite data you can consider. And next, one more thing, evapotranspiration. Evapotranspiration, see, transpiration means the water which is coming. See, transpiration means with respect to plants or trees. So evaporation means with respect to ponds or lakes or ocean. Now, what do you mean by evapotranspiration? So evapotranspiration is nothing but, in a simple sense, some of plant evaporation. Clearly they are mentioning plant evaporation and land evaporation. That means here you can see the image which I have taken from online source. So here you can see there is a plant and there is a surrounding soil. So from surrounding soil the evaporation will happen, and from plant transpiration will happen. That means the combination of both leads to evapotranspiration. So combination of both leads to evapotranspiration. And there will be another some terminologies called potential evapotranspiration and actual evapotranspirations. So measurements and estimation of evapotranspiration, you people can remember there is a lysimeter and Penman's equation and a Blaney-Friedel formula. So these are the measurements and estimation of evapotranspirations. Now we have covered almost interception losses, transpiration, evaporation, evapotranspiration. Now next we will see infiltration. Before that we will go further in terms of evaporation. So what are the measurements we can do with respect to the measurements and estimation of evaporation? So pan measurements, and in terms of empirical, some of the formulas, Fizzolot, and Mayos and Rover, and analytical methods in terms of water budget method. Now we can see the first one, pan measurements. What do you mean by pan measurement? Pan measurement is nothing but how much water evaporates from a small dish. So we are considering some water. So how much it is going to evaporate in a particular area. So we can take a small dish and we can pour some 1 liter or 2 liters of water and we can keep on the ground and we can measure the initial height, and after sometimes you can come and you can check some evaporation. We can see that means it reduced in the level. That is nothing but water is converted from liquid to water vapor. That liquid to water vapor, then it will be transferred to the condensation and again it will come back to the precipitation. So pan evaporation is very easy and simple. So here the some of the formulas they have given. Pan evaporation is nothing but E equal to P plus or minus Z. P is nothing but precipitation and plus or minus Z. Z is nothing but Z is equal to volume of water either you are added or removed and surface area of the pan. What do you mean by added or removed? For example, added is nothing but when you are measuring that means something is added, something is removed. For example, you can see there is a pond. You can see while you can see some kind of rate you can observe constantly if there is no addition or removal of water. If there is a certain rainfall is happened, that is nothing but addition of water. If some amount of water is transferred from one place to other place in terms of usage for domestic purpose from that particular pond, that is called removed. So it depending on that. So pan evaporation is nothing but depending on addition in terms of rainfall, removal in terms of utilization in terms of domestic purpose or agriculture purpose or industry purpose. So here we have to observe in terms of pan. One dish you have to take, pour some 1 liter of water and you observe, just you add it or you remove it in between and you observe what is happening. Next, coming to the point, actual evaporation from water body. So Cp into pan evaporation. Already we are calculating pan evaporation. We know what is pan evaporation, P plus or minus Z, and Cp is nothing but coefficient of pan. So that is actual evaporation by pan evaporation. Actual evaporation by pan evaporation. Pan evaporation is what you measured, actually what is there in that particular area, particular reservoir. So depending on pan coefficients, depending on different areas, they were mentioned the values, like WSB class A evaporation is 0.7, IESI pan, that is modified class A, is 0.8, and Colorado sunken pan is 0.78, and USGS floating pan is 0.80. So usually you can take 0.7 if they are not asking anywhere in your problems. So for pan coefficient you can take 0.7 if they are not mentioning. Depending on particular areas it will be shifted. Now we will see one problem. Calculate the evaporation from a pond. So how to calculate? Please try it from your basic knowledge. So what they have given, if the pan evaporation is 45 mm, the pan coefficient is 0.7, then what is the evaporation in the pond? So what will be the thing? Just look at here. So here Cp equal to coefficient of pan equal to actual evaporation by pan evaporation. So what is the actual evaporation? Now they are asking, actual means pond. Actual evaporation equal to Cp into pan evaporation. What is Cp? Cp is 0.7 they have given. And what is pan evaporation? 45. So that is 31.5 mm. That is the calculating the actual the evaporation from a pond. If the pan evaporation is 45 mm, the pan coefficient is 0.7. So here we can see the answer. The pan coefficient is 0.7, pan evaporation is 45, and pond is Cp into Ep, that is 0.7 into 45, that is 31.5, and the evaporation from a body is 31.5 mm. Now we can see the next question, which is very beautiful question. You people can understand in a good way. So here you people need to understand the question properly, then only you people can solve this thing. It is a very simple question, but it looks like big when it comes to the screen or when it comes to the number of words or whatever it may be. But you can see here, at the beginning of a certain week, the depth of water in an evaporation pan, that is 1.2 meters diameter, was 7.75. So what they have mentioned, at the beginning it was 7.75 centimeters. Okay, that means beginning is 7.75 centimeters. You people can understand. And while during that week, okay, let us finish. During the week, the rainfall was 3.8 centimeters and 2.5 centimeters of water was removed from the pan, and to keep the depth of water in it within a fixed range. So at the end of the week, so initially 7.7, at the end of the week is 8.32 centimeters. Now during this particular week, what happened? There is a rainfall. So there is a rainfall called 3.8 centimeters, and there is a some amount of water is removed, that is 2.5 centimeters. Now you can tell there is a addition, there is a subtraction. That means 3.8 minus 2.5. So what is the value? 3.8 minus 1, that is 1.3 centimeters. Got it? So initially they have told 7.75 centimeters at the beginning of the week. At the end of the week they observed 8.32. In between something is happened. Something is nothing but there is a rainfall of 3.8 centimeters and something they were removed, that is 2.5. So 3.8 minus 2.5 is 1.3 centimeters. Now you people can understand. So where we have to add this 1.3? 1.3 added to the initial week. So what is the initial week? 7.75 plus 7.75 plus 1.3. So that is 9.05. So now you can make final one 9.05 minus 8.32. So the end of the week, how much they asked? They told 8.32. So we will get, what is the value? 9.05 minus 8.32 is 0.73. They haven't mentioned regarding the pan coefficient. You can see here. If pan coefficient is not mentioned, then you have to take directly 0.7. Just multiply 0.73 into 0.7. Then you will get 0.511 centimeters. So this is a final answer what they are understanding. So here in a simplified way, at the beginning of the week it is 7.75 centimeters and at the end of the week it was 8.32 centimeters of water. That is what initially 7.75, finally 8.32. We cannot make it 7.75 minus 8.32, that is equal to some negative value. We cannot do that way. So we have to see what happened in between the week. So during the week something is happened, that is called the rainfall was 3.8 centimeters. That means something is added to the particular point and something is removed, 2.5 centimeters of water. It may be for removed means in some persons, like some terms like maybe domestic use, agriculture, or some kind of hydropower, some other industrial sector they have used. So now 3.8 minus 2.5 is 1.3. Now got a clarity? So 7.75 at the beginning plus additionally some amount of water is added. That is 1.3. 7.75 plus 1.3 is nothing but 9.05. So this is completely at the beginning of the week you have to make. Then at the end of the week 8.32. Just minus it. 9.05 minus 8.32, then you will get 0.73. Then we have to multiply it with, because we have to estimate the evaporation. So 0.73 into 0.7. Then you will get 0.511. For further clarification, again I want to repeat it. Now you can see here, initially 7.75 they given and rainfall 3.8 and 2.5 during the week it happened. So 3.8 minus 2.5, that is equal to 1.3 centimeters. Now here 7.75 plus 1.3. 7.75 plus 1.3 is nothing but 9.05 centimeters. Now you can see 8.32 centimeters. Now evaporation loss is 9.05 minus 8.32. So what is the value? 0.73. So if nothing is given, what is the value? 0.73 into 0.7. So I will write again. It was a mistakenly happened. 0.73 into 0.7. Then we will get 0.511 centimeters. So they are not expecting in terms of centimeters, they are expecting in terms of mm. So what we have to do, just multiply 5.11 mm. So this is a completely solved problem. Initially 7.75 centimeters and there is a issue in terms of water fluctuated in terms of during the week 8.38 and 2.5, and we have done minus and we added it at 9.05 and 8.32. Then we have done with respect to 9.05 minus 8.32, 0.73 centimeters. Then with 0.73 centimeters with respect to 0.75 we got 0.511 centimeters. Then finally we have to convert it into mm, that is 5.11 mm. Now you can see one more problem. It's very simple, but we should know some kind of like dimensions. If 5 liters of water is removed from an evaporation pan, so there clearly mentioned something water is removed. Got it? So 5 liters of water is removed from an evaporation pan of diameter 2 meters, and simultaneously rainfall measurement is 9 mm. Then what is the evaporation? So here we have the net volume of the water is nothing but volume is nothing but area into that is in terms of meter cube we can write meter square into meter, that is area into, so area and into some meters is nothing but precipitation minus evaporation. So if we know able to convert liters into meter cube, then 5 liters is nothing but 0.005 meter cube. So pan diameter is 2 meters. In a simple way we can write it as pi by 4 t square, and precipitation 0.009 mm, sorry meters, and it is evaporation. Finally we can come with this one simple basic thing, a volume. If you know in terms of how to calculate volume in terms of meter cube, just we have to make the basic definition and we can wind up like it is in meters and we have to convert it into mm. So finally we will get this thing. So that's it. We will see the next topic with respect to infiltrations. So now next one, infiltration. So now we can see the infiltration. Before going to see the infiltration, we can understand first there will be kind of precipitation. After precipitation you can see some kind of losses, evaporation, transpiration, evapotranspiration. In terms of losses, afterwards you can see some kind of runoff and groundwater recharge. These groundwater recharge having some stages. One is infiltration, another one is percolation, another one is groundwater table. So that means the water from surface on the ground, this is ground level. If it wants to go to groundwater table, there are multiple stages. So first stage is infiltration, second stage is percolation, and after percolation you can see groundwater table. So that means it is purely the water rain it is coming, it is purely depending on the soil, the type of the soil and forest area. So now we'll see. So as I mentioned, infiltration. So infiltration is a method or process by which water can get into the surface strata of earth. Simply it is the water. For example, here there is a rainfall. So it need to go. It will go only things like there should be some pores or there should be some gap. We can tell gaps. So then only it will reach to the bottom. Otherwise, how this forest will help us means, because this is a like there is nothing is there, and here we can see one kind of tree, and here you can see there will be some roots. Every tree or plant, everything will be roots. These roots initially you can see here there is nothing is there gap, but these plants will create some kind of gaps. That means whatever the rainfall is happen, it will be having some gaps to flow from top to bottom. So that means that's all. If forest area is more forest area will leads to more infiltration, because of it is creating the gaps in that particular soil. So now soil moisture deficiency. So definitely if we cannot grow plants in where there is not meeting the soil water deficiency, soil moisture deficiency. Soil moisture deficiency happens when there isn't enough water in the soil for plants to grow properly. So it can be caused by low rainfall or high evaporation or poor soil that doesn't hold water well. So it can be caused by low rainfall, high evaporation or poor soil that doesn't hold the water well. Now you can see after meeting, that means after meeting soil moisture deficiency, then only the water, if any excess water remains in the ground, flow vertically deep into the ground and join the water table. So after meeting soil moisture, then it will go down. That is called infiltration, as I mentioned. Next, percolation. Then groundwater recharge. So these all things are there. So now we can see the deep vertical movement of water. That means, as I mentioned, first it will be infiltration, second it will be percolation, third it will be groundwater recharge. So percolation means deep vertical movement, means the water is passing from ground to infiltration, and after certain extent again it will go back to the percolation stage. After finishing the percolation stage only, then groundwater table we can see the recharge. So many factors will influence depending on that. So major factors are temperature. Obviously, if temperature is high, as I mentioned in it is particularly infiltration is depending on trees or plants kind of forest area. If temperature is more, it is very effects for sensitive plants which cannot sustain and which cannot make the growth of the root. If root is not up to the mark, then there won't be any kind of infiltration. So this will affect it. And vegetation, that indirectly it is, directly it is telling, depending on the vegetation it will vary. And soil texture and soil structure. That means, for example, if that particular soil is compacted, then there won't be any kind of water to flow from ground to surface to ground, because it is already compacted. That means all the pores are filled in that, then there is no gap to flow. So at these circumstances, the water will restrict on the above, and it cannot encourage infiltration or percolation or else any kind of groundwater. So depending on the soil structure also it will be there, soil texture also it will be there, and depending not only the things, depending on precipitation intensity and duration also. And finally, soil moisture content. As I mentioned, we have, if soil moisture deficiency is there, it is very difficult to attain the infiltration things. So some factors indirectly affecting, that is land use and management practices and water quality. See, as I mentioned, if forest area is there, more infiltration. If that forest area is not there, that means forest area is converted to urban area or else agriculture, then infiltration will be less. In the same way, water quality, if water quality is not good, then the bottom of that particular water, it will be completely clogged. That means it will completely having one kind of a layer which will obstruct to infiltrate into that particular soil. So water quality is also matters when it comes to the infiltration. And not only that, topography means depending on the elevation, the infiltration will change. And coming to the climate and weather patterns. So now, before going to the before going to the infiltration in depth, I want to clarify some kind of Indian standards, what they are using. I want to show you Indian classification soils. For example, fine soils won't encourage much infiltration when compared with coarse and very coarse soil. There itself, you people need to understand some dimensions I have given. Greater than 300 mm and less than, you can imagine the particle size, less than 0.002 mm diameter of the particle size, which is fine. That means that much particle size are closely attached near means the water cannot flow. It will flow, but it will take some more time when compared with coarse, very coarse soils and coarse soils. It will having the capacity is more when comparatively, like coarse soils, medium soils and fine soils. So this classification, when I am going to tell in next upcoming slides, clay soil, sand soil. For example, you see clay and sand. Now comparatively, clay is having less infiltration when compared to sand. Now silt and sand. So sand is having less infiltration capacity when compared to sand, like that. Now sand and gravel you compare. So sand is having less infiltration capacity when compared to the gravel, like that. So next to some terminologies which is related to geotechnical, like geotechnical engineering, we need to understand the basics about the soil, dia of the soil. This we can see in terms of, this is a soil in terms of clay. This for image analysis, this is a clay and this is a loam, and this, as you people know, sand desert region, and this clay, and this is a gravel. So different, not only mentioning the classification but also mention the images to properly understand what is that. Now the classification of infiltration capacities. See, for example, you can see here, as I mentioned, clay. Clay is having very low infiltration. As I mentioned, clay is having less when compared with sand, when compared with gravel, when compared with silt. So here also, after doing some kind of analysis, they come to know that less than 2.5 mm per hour infiltration capacity. When compared with sands, you see here 25 mm per hour. That means here itself you people can understand, clay is not encouraging much infiltration, whereas sand is encouraging good infiltration. And there is a called new terminology again we got, LOAM. Again, once again I will write. Loam. Loam is nothing but combination of silt, sand, clay. That is which percentage of the, for example, clay is dominated, clayy loam. Silt is dominated, silty loam. Sand is dominated, sandy loam. So this kind of things will come. You can see sandy loam. That means there is a combination of clay, silt, sand, but in that particularly sand is dominated. So now we are going for next one. What are the measurements of infiltration? So measurements of infiltration are three types: infiltrometers, rainfall simulators, hydrograph analysis. Infiltrometers. The first one, infiltrometer. There are two kinds of infiltrometers: single ring infiltrometer and double ring infiltrometer. Single ring infiltrometer, double ring infiltrometer. So single ring infiltrometer means, here image you can see, this is single ring infiltrometer. Some dimensions you can see here, 300 mm and 200 mm. And here a single ring infiltrometer is a metal ring inserted into the soil to measure how quickly water infiltrates. It's a device used to determine the infiltration rate of soil. That means simply this is a device. You have to take this instrument and you have to pour some level of water. Then you can see after some time there will be some kind of infiltration will happen. That means here just we are taking 1 liter of water. After, for example, 1 liter of water, then after some time we can see there will be some water will be lost in terms of recharged in terms of ground. So there will be another kind of infiltrometer is nothing but double ring infiltrometer. Previously we have seen only single, now they made it double because of some leakages of water is happening here. So they want to protect it, they made it a double one. Now is used as a field, this obviously this is a field instrument only, and which water infiltrates into the soil by two concentric rings as inner and outer that are partially inserted into the ground. So our final agenda is what is the infiltration. That is only the way we can see. And rainfall simulator. Rainfall simulator means it's a laboratory one. Previous one infiltrometers are field. Now rainfall simulators are laboratory. Here what they have written, you can see a rainfall simulator is a device that produces artificial rainfall to study how soil and other surfaces react to rain. That means here they clearly mention artificial rainfall. So artificial rainfall is nothing but we cannot go, we can go to the field and we can find some kind of infiltration things, but if you want to understand different, like what is a, for example, here you can see different kinds of variations in the intensity and duration of rainfall, we can use this laboratory and with respect to the different kinds of soils. So now hydrographic analysis is also one of the thing where we can use. Infiltration refers to the water soaking into the ground, reduces the surface ground, and reasonable estimation of infiltration capacity of a small watershed can be obtained by analyzing runoff hydrographs. This will be covered in the next upcoming slides. Hydrograph, don't worry, I will explain there, and corresponding rainfall records. So however, that in a simple way, hydrograph analysis, you can make it a like a time versus discharge. So discharge means runoff. Runoff means after meeting the requirements of infiltration, then only the runoff will generate. So some of the estimation parameters of infiltration models are there. So here we can discuss Horton's equation, Phillips equation, Kosciuszko equation, and Greenamt equation. They are very important because understanding the infiltration is very critical. If we are not able to measure properly the infiltration, then we are not going to get good result of runoff. That means hydrographs we cannot get good. Now coming to the first one, Horton's infiltration capacity, Horton's infiltration curve. So we can see Horton's has conducted infiltration studies in his laboratory on different soils and concluded following things. Infiltration capacity is maximum at the beginning of the storm and it exponentially decreases as the storm decreases. That means in a simple way I would like to explain with one graph so such that you people can understand easily. So Horton's infiltration capacity, now you can see this is two ways, time versus infiltration. Now for example, every time you can see whenever the rainfall is occurred, the first one is the soil will, whenever the rainfall is occurred in that particular area, the soil will absorb the water initially. It never ever encourages initially itself runoff until unless it is saturated zone. So whenever rainfall is occurred, then it will encourage us to take water with respect to ground. After fulfilling the criteria only, it will allow us to run off to meet the other requirements like ponds, lakes. Then only we can see evaporation, transpiration, all the things. So here Horton's has clearly mentioned infiltration. That means whenever rainfall occurred, you can see one good thing that infiltration will be more at the beginning, because obviously whenever rainfall happen, first water will try to take to ground. Then only it will take. That means infiltration rate is more at initially, then after certain time it will be constant. FC is nothing but constant, FC naught is nothing but initial stage. That means why constant? Obviously after getting the constant position only, it will ready to encourage for runoff. That means no more it is going to take the water and it is saturated, then it will be encouraging for the runoff, and from the runoff you can see ponds, lakes and everything will be fulfilled. That means FC naught is comes to the initial infiltration and FC is final infiltration rate. Now we can, for example, I would like to know at some places, I need to know here, what is the infiltration rates. That is nothing but it is denoted by FCT. So obviously you can write FCT equal to final infiltration rate. We know the final value, we know the initial value. This is the initial value, this is the final value. Final infiltration rate plus FC naught minus FC into, this is an exponential curve. So obviously e power minus KT. So we will see in a precise way, FCT equal to FC plus FC naught minus FC into e power minus KT. So now this is FC naught also equal to F naught, don't get confused. FC naught equal to infiltration capacity at time T. Obviously at time T it will be peak, and FC is a steady, I told steady or constant, whatever it may be. This is this part, and infiltration capacity at the time. So infiltration capacity at the time is FCT. Next exponential, in exponential e power minus KT you can see some kind of T. K. That K is nothing but infiltration rate constant, or in another way you can make Horton's decay coefficient. So what is the infiltration rate? E power minus kt. Now using the Horton's infiltration curve, total infiltration in given time t as well as the infiltration between any two periods can be worked out along with the actual rate of infiltration. Now, for example, as you people know FC naught, this is FC and this is time. So now if I want to know a particular stretch, then just use it FCT into dt. If I want to know at first half of the section, then you have to make first half mean there will be 0 to, for example, 2 hours. Then you just make integration of 0 to 2 FCT into dt. Next, if you want to know about in between, not the first half, but if you want to know about the next half, for example, it is 2 hours to 4 hours. Then integration of 2 to 4 FCT into dt. Got it? First, if you want to know, calculate at particular location, then try to use this formula FCT into dt. If you want to know first half of the section, integration of 0 to t into FCT into dt. Next half section, integration of 2 to 4, that is some ti to ti plus 1 into FCT into dt. For example, if I want to know entire area of the infiltration, that combination of first half, second half, intermediate half, everything, then there is a formula called FC into T, it is not FCT, plus FC naught minus FC by K. This formula is derived based on this thing. If FCT is equal to FC, that means we are not calculating anywhere. Our focus is that obviously we know this is FC and we are calculating at particular point. If this FCT is also value also equal to FC, then only you have to use this formula. That is, there is no where that is a completely steady state. So it's a completely steady state, that means constant. Now characteristics of infiltration curve, you can understand initially the infiltration rate is high due to dry soil conditions. Over time, as the soil becomes saturated, the infiltration rate decreases exponentially and approaches a constant rate. And next, the rate of decline is controlled by soil type, texture and compaction. Now graphical representations, you can see the curve is steep. Obviously, at the beginning, the curve is steep at the beginning. Why? Because infiltration is more at the beginning and exponentially decay. And here as I mentioned, I am using clay and sand many times. If clay soil is there, low infiltration we can see. If sand is there, high infiltration we can see. That's what I given the classification before itself. Now, what are the factors affecting Horton's infiltration curve? So, soil properties, surface conditions, rainfall characteristics. So, these three are the things which are affecting the infiltration. There are more things also there, and applications. Rainfall runoff models, soil water conservation studies, and hydrological modeling in watershed management. We'll see one kind of problem regarding Horton's infiltration, then we come to know what is happening here. So here the Horton's infiltration equation for a basin is given by F is equal to 6 plus 16 into e power minus 2t, where F is in mm per hour and t is in hours. What are the values of F naught, Fc and K? So now first we have to note down what is the standard thing. FCT equal to Fc plus Fc naught minus Fc e power minus Kt, right? This is a standard one given by Horton's. Now what they are asking? Just write it down here. F is equal to 6 plus 16 into e power minus 2t. They need some values. So directly we will get what is the FC? FC is equal to 6 we got. What is K? K is equal to 2. Then what about FC naught? So we need to know only one value, that is FC naught. So what is the condition for FC naught? FC naught equal to FC naught minus FC equal to, what is the value FC naught minus FC? 16. So FC naught equal to 16 plus FC. Then FC naught equal to 16 plus 6, that is equal to 22. So now we got all the values. FC equal to 6, K is equal to 2, and FC naught equal to 22. Got it? So just we have to memorize the formula, then we will get the answer. Next, one more problem. The parameters in Horton's infiltration equation, already they have given the standard formula FCT equal to FC plus FC naught minus FC into e power minus KT, are given as FC naught value they have given directly, that is 7.62 centimeters per hour, and FC value also given 1.34, and just K value also they are given 4.182 per hour. For assumed continuous ponding, what is the cumulative infiltration at the end of 2 hours? So now what do you mean? Just stop the video, just pause the video, and please try to solve by yourself such that you people can understand what is happening. Because here just everything they have given, but something they are asking in terms of, for assumed continuous ponding, what is the cumulative infiltration at the end of 2 hours? So they are targeting 2 hours, that means T equal to 2. Okay, let's solve this thing. So now we have to make it in FCT equal to F of 2 equal to, that means at particular 2 hours they are asking. As we know, this is there, at particular 2 hours they are asking, if it is a Horton's one. And then just substitute it, FCT equal to FC plus FC naught minus FC into e power minus KT. Now just substitute F2 equal to, what is the FC? 1.34 plus FC naught 7.62 minus FC 1.34 and e power minus, what is the K value? 4.182 into, at what is the duration they are asking us to find? At the end of 2 hours, just put it 2, and you can see what is the F2 value, just calculate it. 1.34 plus 7.62 minus 1.34 into e power minus 4.182 into 2. So we will get the value F2 as 1.34. So somewhere this equation is interlinking. FCT is equal to FC. Then you have to use fourth condition. FCT means, FCT is nothing but F2 FC. What is the F2 value? 1.34. What is the FC value? 1.34. I would like to show where is that. Here you can see when FCT is equal to FC, then only you have to use this particular formula to get directly solution of the things. Now you can use that end product formula. So FC into T plus FC naught minus FC by K. What is FC? 1.34 into, what is the time? Time is 2 hours plus FC naught 7.62 minus FC is 1.34, then divided by 4.182. That is nothing but, if you calculate, you will get 4.182 centimeters. So this is the final one. Just we will cross check the answer. FT or FCT or both are one. FCT, then just we have to substitute the values, then 1.34 we got. At particular FCT, when FCT is equal to FC, then only we can make it as a steady condition. So when we are getting steady condition, then only we have to apply this formula. This formula is very important when we are going with steady conditions. FCT into T plus FC naught minus FC by K. Then we will get the final end result. Some anywhere if they are mentioning the in question steady or constant, then you can use directly this equation. Okay. One more problem we'll see. Now, a 24-hour storm occurred over a catchment of 1.8 kilometers square. So something they have given some area and the total rainfall absorbed was 10 centimeters. An infiltration capacity curve is prepared and it had the initial infiltration capacity of 1 centimeters per hour and attained a constant value. Here we can observe there is a constant value. Constant itself defines steady. So steady means we have to use directly fourth formula. That means here you can see fourth formula FC into T plus FC naught minus FC by K. Fourth formula, then you can see, and here something they are mentioning 0.3 centimeters per hour after 15 hours. That means after 15 hours it will become steady and it will be having some rate called 0.3 centimeters per hour with a hot tons constant K. So with a hot tons constant K, 5 hours per hour, and IMD, Indian Meteorological Department, pan installation in the catchment indicated a decrease of 0.6 centimeters in the water level after allowing for rainfall during 24 hours of its operation. You have to be careful. 24 hours is different. In the 24 hours, 15 hours is getting the constant. Other losses were found to be negligible. So they are not worrying about the other losses. They are only worrying about the things. Determine the volume of runoff from the catchment. Catchment or basin or watershed, anything is one, because why they are telling runoff from catchment means already they have given 1.8 kilometers per hour square kilometers of area. So definitely we will get some value and we have to multiply and we will get the runoff. So assume a pan coefficient of 0.7 as I mentioned in the early previous lectures. You can see if anything is not given, just assume 0.7. Got it? Let us solve this problem. In 24 hours rainfall, as I mentioned, it is 24 hours and rainfall is 10 centimeters they have given. In 24 hours evaporation means CP into pan evaporation. If CP value how much? 0.7, and what is the pan evaporation is 0.6. So here we can see 0.7 into 0.6, that is nothing but in 24 hours this is the evaporation rate. And in as already mentioned, it is in steady state. So directly you can use this thing FCT into T plus FC naught minus FC by K. So what is the FC value? FC value at 15 hours. You can see there is a constant in the question. You can see. See 0.3, but you do not mention 0.1 into 24 hours total. But it is happened steady at 15 hours. 15 hours, but our problem is with respect to 24 hours. Here they can mention. So 24 plus 1. What is the 1? Initially they have given 1. 1 minus 0.3 by 5. 7.34. Now you can see the runoff. Runoff is P minus E minus I. So runoff is nothing but whatever the precipitation we have, we can see in, and in terms of evaporation, infiltration losses, if you remove, that is called precipitation. As I mentioned, inflow minus outflow is equal to change in the storage. So our runoff equal to P minus E minus I. Runoff equal to P means 10, they have given, E means 0.7 into 0.6 and I means 7.64 we got from steady state just now. And total is 2.24 centimeters, that is nothing but the runoff depth. So we have, they required only runoff volume. Volume is nothing but area into depth. Area into depth, that is volume. So now area is 1.8 kilometers square, that is 1.8 into 1000 square into 2.24 by, it is in meters, so this is in centimeters, convert it into meters divided by 100, that is 100 centimeters equal to 1 meter, but we need 1 centimeter equal to 1 by 100 meters. So in book they have given 2.24 centimeters. That means this can be rewritten as 2.24 by 100 into 100 meters. That's it. We can see one more problem. The infiltration capacity in a basin is represented by Horton's equation as FCT equal to, is an purely integration one, 3 plus e power minus 2t. So they are asking what is the first 30 minutes duration and next 30 minutes duration, what will happen to the storm. Now you can see, if you know the basic integration formulas, it is very easy. Even though if it is not that, just remember only two formulas: e power ax into dx equal to 1 by a into e power ax by 2. E power ax into dx equal to 1 by a into e power ax plus c, and integration of dx equal to x plus c. If you people can able to memorize these two integration formulas, then it is very easy. Now they have given some kind of thing, 3 plus e power minus 2t. Just first half section, that means 30 minutes is can be written as 0.5 hours. So 0 to 0.5. And they have given in question 3 plus e power minus 2 to just take the integration upper lower limit, upper limit, just do it like 3 into dt is nothing but this will comes with respect to this thing, that is integration of any constant is nothing but 3 into t. So this you can get, and integration of e power ax means this one, integration of minus 2t means 1 by 2 into e power minus 2t. Then just substitute upper limit minus lower limit, then you will get 1.816 centimeters. In the similar way, just change the limits, 30 minutes to 1 hour, that is 30 minutes is nothing but 0.5 hour. Then you can change the make it a lower limit, upper limit, then do the integration, then you will get 1.616 as the final answer. Now you can see some kind of other things other than Horton's infiltration. There is another one called infiltration indices. In hydrological calculations involving floods, it is found convenient to use a constant value of infiltration rate for the duration of a storm. So the defined average infiltration rate is called infiltration index, and two types of indices are in common use: phi index, W index. So we come to know two things: phi index, W index. Let us discuss what is phi index. Phi index is the average rate of infiltration, assuming that all rainfall above this rate becomes runoff. That means phi means P means total rainfall, R means runoff, and T means duration. Just phi is equal to P minus R by T. Just remember it. And W index is nothing but modified phi index, just P minus R minus I by T. They have introduced only the losses, only the initial infiltration losses. Difference from phi index is more accurate because it accounts initial losses before steady infiltration start, suitable for irregular rainfall events. Now we can see one small problem regarding indices. The total absorbed runoff volume with a during a 4-hour storm with a uniform intensity is 2.8 is 25.5. That means just write what they have given. I is equal to 2.8 centimeters per hour. Got it? And volume they had mentioned 25.2 into 10 power 6 meter cube. And one more thing they have given, T is equal to 4 hours. And one more thing they have given, area. Area is equal to 280 kilometers square. Now P is equal to I into T. So P is equal to I means 2.8 into T means, what is the T? 4. So total 11.2 centimeters. So we got the rainfall. Next our agenda is to volume equal to area into depth. Volume equal to area into runoff depth. What is the runoff? Runoff equal to volume by area. This one more thing you please remember, try to remember it. So now runoff equal to, what is the runoff? Volume by area. What is the volume? 24 by 2 into 10 power 6 by, what is the area? 280 kilometer square. Kilometer square means 1 kilometer equal to 1000 meters. That is 1000 square. Then you will get runoff equal to 9 centimeters. Now you can find the phi index, the average infiltration rate. Phi is equal to P minus R by T. Our agenda is to find P. So we got P is equal to I into T formula. Next our agenda is to find R. R is equal to volume by area. So just substitute is phi is equal to P. What is the P? Final one, 11.2 minus, what is the R? R is nothing but 9 centimeters we have calculated with respect to volume by area. And what is the T? T is having 4 hours. Now what is the phi index? 0.55 centimeters per hour. So this way everything is interconnected. So phi index is interconnected with precipitation, runoff and duration. And precipitation is nothing but P is equal to intensity into time. So P is equal to I into T. And runoff is nothing but V by A, that is volume by area. So next problem you can see, a storm event recorded total rainfall of 100 mm over 4 hours and the measured runoff was 40 mm and initial loss was estimated at 10 mm. Determine the W index. So just we have to note down the given data. P is equal to 100. Obviously they have mentioned rainfall. Next T is equal to 4 hours. And next runoff equal to 40 mm. And next infiltration loss is equal to 10 mm. So now which formula we have to apply? Phi index or W index? So it is showing some kind of losses. Obviously we have to apply W index. So what is the W index formula? W equal to P minus R minus I by T. So W equal to, what is the P? 100. What is the R? 40. What is the initial losses? 10. What is the duration they have given? 4. So W equal to 100 minus 40 minus 10 by 4. That is equal to 12.5 mm per hour. So now you understood? W is equal to P minus R minus I by T. Okay. Next, P is nothing but 100, R is nothing but 40, I is 10, then hours are 4. So 100 minus 40 minus 10 by 4. Now next question. In a particular season, a catchment was found to have a phi index of 0.5 centimeters per hour, and if a rainfall of 2 centimeters occurs in that season at a uniform rate in a 6 hours storm, what is the direct runoff? So please try to solve it. So first try to note down the things. So here the given data is directly they have given phi is equal to 0.5 centimeters per hour, and next value they have given p is equal to 2 centimeters, and t is equal to 6 hours they have given, and runoff equal to, they are asking us to find the runoff. So please try to find it. So everything we know, just substitute it in the formula. So now you can see the formula phi is equal to p minus r by t. So already they have given what is the phi, 0.5, what is the p minus 2, and runoff we need to find, and what is the value of duration, 6 hours. So runoff equal to, what is the value of runoff? Minus 1 centimeters. See, runoff never ever been in terms of minus 1 or minus 2. If there is no runoff, just we have to keep it as 0 centimeters. Instead of we are getting minus 1, but you just make it as 0. So there won't be any kind of minus 1 or minus 2 centimeters. So one more problem we can see. So here they have given t is equal to 3 hours. Okay, and they have given some 1.6, 3.65, 2 and 2.2 and 1 in terms of I. So there is a simple formula, p is equal to I into t. What is the I? Intensity is 1.6, 3.65, 2.8, 2.2, 1, and t is hours. So hours means there are 6 storms there. So now 3 hours is divided into 0.5 hour, 0.5, that is 0.5 plus 0.5, 1 hour, again 0.5 hour, 0.5, 0.5, 0.5. That is all cumulatively you will get 3 hours. Now we can see they have given directly R value, no need to worry. So just we have to find P. So P equal to 1.6 into, so what is the intensity? 1.6. What is the duration? 30 by 60 plus 3.6 into 30 by 6, because equally we are dividing the duration, plus 5 into 30 by 60 plus 2.8 into 30 by 60 plus 2.2 into 30 by 60 plus 1 into 30 by 60. So finally you have to multiply all the things and you will get the value as 8.1 centimeters. So in a simple way, if I want to tell you I into T, so P equal to I into T, the basic formula which we have solved previously, P is equal to I into T. Got it? Now you can get pi value as 8.1 minus 3.2 by 3 hours. So you can check 1.63 centimeters per hour. Now, whether it is satisfied or not, whatever result we got, it is satisfied or not, to cross check again we have to go through the initial one. So here the value they have given 1.6, right? The value is 1.6. Just check how many values are less than 1.6 in a given question here. So 1.63, so 1.63 less than 1.6, yes, 1. So this is 1. 3.6 is greater and 5 is greater, 2.8 is greater and 2.2 is greater, and this thing is less. Now you just eliminate those two things, again you do the same thing, but here you are eliminating 1.6 and 1. Definitely there will be total duration is 2 hours, because 3 hours duration for entire thing. Now we have eliminated 1.6 and 1. Definitely it will be only 4 things are there in terms of intensities. If 4 intensities are there, that is 2 hours. Now again you equally distribute it. 3.6 into 30 by 60 plus 5 into 30 by 60 plus 2.8 into 30 by 60 plus 2.2 into 30 by 60. Now you will get one kind of value, that is 6.8 centimeters. Now you can see the pi value P minus R by T. That is, the P is equal to how much? 6.8 minus R is equal to 3.2 by here 2. Why 2? Why not 3 hours? Because we have eliminated 1.6 and 1 centimeters per hour, because they are coming less than 1.63 from our trial 1. So you can make it as, this is as a trial 1, this is as a trial 2. Now phi is equal to P minus R by T. So pi is a P value we got, that is 6.8 in terms of P is equal to I into T, and runoff 3.2 and T is 2 hours. So totally we will get 1.8 centimeters per hour. So don't stop here, again you cross check it. The remaining value is what? 3.6, 5, 2.8, 2.2. Now you see whichever is less than 1.8, you just eliminate it and do the third try. 3.6 is greater than, like 1.8, you compare, 3.6 is more, 5 is more, 2.8 is more, 2.2. Now you can stop here. Now the problem is solved and you can stop here, because until it satisfies we have to go for trials, pi 1, pi 2, pi 3, pi 4, pi 6, like that we have to keep on, we have to increase it. So that is the way we have to solve this kind of problems. And finally, again, once again I am showing this water cycle. Here you can see first component, precipitation we have completed, right? Next, infiltration we have completed, right? And evaporation, transpiration we have completed, and condensation we have completed. Now only one leftover part before going into the analysis, which is very important, is runoff. So now runoff we will see. Yes, we will see what is runoff and what are the factors affecting runoff, and why it is important to study, and everything we will come to know in the upcoming slides. So now in a simplified way I have given the definitions for runoff. So runoff means a draining or flowing of a precipitation from a catchment area through a surface channel. Understood? Understood? I'll give a simplified. See, there is a watershed. This you treat as a outlet, that is meter cube per second. Now whatever the rainfall is happening in this area, obviously, for example here rainfall, it all will collect the rainfall and it will keep at one particular area. Runoff means draining of flowing of a precipitation from a catchment area through a surface channels. For example, here you can see some kind of rainfall. This water will go to this river network and this will join to here and this will join, keep on increasing the things. Okay. Now runoff is that portion of rainwater which ultimately joins streams and rivers. Obviously I told first it will collect to sub tributaries, next tributaries, next main river. This is the pattern. What is the sub tributaries? This is the sub tributaries, this is the tributaries, this is the main channel. Got it? And it is an output produced by the catchment for a given input of rainfall. That means whatever the rainfall is happening, after the losses, whatever the remaining water is flowing on the surface, that is called runoff. Now we can see some types of runoff or classification of runoff. Surface runoff or overland flow, and interflow and groundwater flow or groundwater flow. So here surface runoff or overland flow defines the flow at which the flow that travels all the time over the surface as open channel flow and reaches the outlet. That means we can see on the surface of the water. And interflow is nothing but it is in terms of particularly infiltration. In particularly it will happen infiltration laterally flow through upper crust of the soil and return to the soil at some location. And groundwater runoff or groundwater flow is nothing but the part of precipitation that undergoes deep percolation. That means first infiltration, next percolation, as I mentioned, next it will go to the groundwater table reaches and the groundwater. In a simplified way, if I want to show you in an image view, so precipitation, rainfall, so we can see some amount of transpiration or evapotranspiration losses. Then you can see this on the surface we can tell overland flow, just below that we can tell through, that means subsurface flow, and here groundwater also will come back to the surface, that is called base flow. That is nothing but here you can see overland flow is nothing but surface runoff, and it is also known as subsurface flow or interflow. And there will be classification for runoff. So direct runoff as well as base flow runoff. Runoff without much delay in joining the stream. It includes surface runoff or overland flow. And prompt interflows, channel flows, everything comes under interception, it comes under direct runoff. And coming to the base flow, so base flow, here we can see the runoff joins lately, that comes under the like base flow, and delayed interflow and groundwater flow. The classification, like three classification: perennial, non-perennial, and epiperennial. Perennial is nothing but the continuous flow of water in that particular river that you can take in terms of if it is having any kind of snow kind of contribution, then we can tell it as perennial. Non-perennial is purely depending on the seasons, and epiperennial rivers are with respect to the short period that you can see in terms of desert regions, that is temporarily streams which cannot be contributed to the groundwater recharge. And next one, some factors which are affecting runoff are direct factors, indirect factors we can see. So direct factors are rainfall intensity and duration, and soil moisture. Obviously the soil moisture will play the key role, and lands as well as land slope and impermeable surfaces. If more impermeable surfaces are there, like in terms of urban areas, you can see more runoff. And coming to the vegetation cover, if vegetation cover is more, like forest area is more, there will be less kind of runoff. If forest area is less, the runoff will be more, and the drainage network, as I mentioned, if drainage network is more, the runoff will be more. If drainage network is less, the runoff is less. Depending on the slope, if slope is more runoff we can see generated. It can you can see it in a hilly terrain areas. And soil saturation also depending on the runoff and intensity duration. And some indirect effects which can be considered, like in terms of long term or secondary impact on runoff. There you can see climate change and deforestation. Climate change actions, you can see it is affecting on the watershed. And deforestation, obviously if you are deforesting, the runoff will be more. And urbanization, increasing in urbanization also, it will be more. And soil erosion also occurs with respect to the deforestation effect, and groundwater depletion in long term effects, because more extraction than recharging if we are doing, then groundwater depletion will happen. And agriculture practices, if the intense agriculture if we are doing depending on more water from groundwater, then there will be a issues with respect to runoff. And some kind of estimation methods are there. So rainfall runoff relation, it's a simplified way of rainfall fitting a linear regression. However, this formula is not applicable only in regions where it is derived. Only it is applicable that regions where it is derived, and it is not derived in other regions. So some empirical equations you can say: Bennett's percentage used for catchment in Vidarbha and MP, and Barlow's table for catchment in UP, and Strange's table for catchment in Karnataka and Maharashtra. And this one more, they were derived in time of English and Geosa's formula, where this were be done in 53 sites in western India, and they have concluded the formula runoff equal to 0.85 p minus 30.5. And in Deccan Plateau, they have given R is equal to 1 by 254 p into p minus 17.8. So these two formulas are were given. And one more thing, Kosla's formula. So Kosla's has analyzed the rainfall, runoff and temperature in terms of monthly basis, and suggested a formula and derived. It is nothing but M here, everywhere M defines monthly runoff, monthly rainfall, monthly losses. And there is a monthly losses, they have given one kind of formula is not 4.48 Tm, and for Tm is greater than 4.5 degrees centigrades. And they have given some conditions. LM is greater than PM, then we can set LM is equal to PM. If PM is equal to greater than LM, we can set LM and PM. That are the some basic things when we are going to solve the problems we can understand. But here the major thing is that if temperature is greater than 4.5 degrees centigrade, then you have to consider LM equal to 0.48 into Tm. Other than that, you should not consider. If it is less, we cannot consider, we have to take directly. Now, method to estimate runoff. So, watershed simulation, yes, obviously with respect to the water cycle, we can see the runoff equal to precipitation after losses. Evaporation, transpiration, evapotranspiration, and coming to the infiltration. And this we have discussed from the beginning. And next one is soil conservation service number. There we can get a direct runoff value, and hydrographs also, and infiltration indices also we will get the runoff value. Okay, now next topic, hydrographs. So hydrographs, name itself suggests we have to make a graph with respect to water. That means duration with respect to discharge. Discharge is nothing but there is a kind of watershed where you can measure the discharge at the outlet location, that is meter cube per second, and you can get some kind of curve like this. That way, this is a curve. This is a curve. Discharge, time versus discharge. Hydro means water, and this is a graph we can see. And now coming to the point, hydrograph basic definition. Hydrograph is, as I mentioned, it is a between discharge and time. So just to understand how much amount of water is running away from the watershed after meeting the losses. After meeting the losses in the sense like evaporation, transpiration and evapotranspiration, and fulfilling the criteria like ponds, lakes and infiltration, as well as the groundwater recharge, and the rest whatever the remaining water which is on the surface and connecting to subtributaries, tributaries and main rivers, and that is collected at the end of the outlet, that is called this one, this is called outlet for this entire basin. It is collected and that is recorded according to the requirement. It may be daily or it may be hourly. So this is one kind of hydrograph where if you have taken initially the higher, here you can take this is a base flow. So base flow, and initially obviously it will be the low runoff. Why it will be the low runoff? Because whenever the rainfall occurred, you can see the initial stage more infiltration will happen. That's what Horton's curve, just now we have discussed about the Horton's curve. Horton's curve initial FC naught will be more, after that steady state FC will attain. So after attaining FC as a steady state, then only the runoff will start accounting. That means after infiltration the runoff will start. So runoff also will start slow and steady, like slowly it will start and it will touch to at one end, that is called peak, that is called peak runoff. Then again slowly it will going to collapse. That means this part is very crucial to understand or to manage any kind of watersheds. It's a just shows the distribution of runoff, but it is very crucial in management and it measures the catchment response of the storm. So some factors which are directly related to affecting the hydrograph, those are the things are nothing but, as I discussed, now you can see this thing, this is a watershed. Now this watershed, you can see depending on the watershed, like as we mentioned in the beginning of the lecture, drainage basin will behave differently with respect to the land use, land cover, slope, soil shape, size, as well as drainage density and all other characteristics. It will respond the drainage basins. In the similar way, hydrographs also is responded, because if there is an area which is completely dominated with respect to forest area, so you can make it as a forest area. So definitely obviously forest area is more, means infiltration will be more, and coming to the point of runoff it will be less. When it comes to the urban areas where you can see the infiltration is less, because of the impervious pavements and constructions which we can see in that particular area, so there will be very less chances of the infiltration and very more in terms of runoff. That's what we can see the urban floods, a separate topic which we can study. So this all why it is happening means depending on the characteristics or the depending on the of the basin as well as the factors affecting the hydrograph. Now you can understand the shape of the basin, the size of the basin, slope of the basin, as well as the nature of the valley. And another two more things, elevation and drainage density also will plays a crucial role in terms of hydrographs. So now infiltration characteristics also makes the similar change. For example, if you are converting land use, land cover, for example, there is a land called forest area. So forest area initially it will encourage us to make good in terms of infiltration. But if you are changing the forest area to urban area, then it is not encouraging infiltration and it is encouraging runoff. So there is a direct impact towards it. And soil type, as I mentioned, soil type means if clayey soil will allow less infiltration rate when compared to the sandy soil, and geological conditions. And moreover, we can see the things called lakes, swamps and other storages. And that means depending on the quality of water Quality of water also will depend. If quality of water is good, then it will be infiltration will be good. But if it is in the criteria of quality of water is not good, and the settlement on the bed will be very it will less in terms of infiltration. Characteristics means cross section, roughness, storage also will plays a crucial role. And other than these things, there are the climatic factors which you can observe. What is the rainfall? That means type of precipitation obviously matters, and intensity and duration, magnitude, as well as the movement of the storm. These all things criteria will play a crucial role in terms of hydrographs. That means if an hydrograph is having more runoff or less on runoff, it depending on the climatic factors like precipitation, intensity, duration, magnitude, and movement of storm. And another thing is that initial loss. And this is evapotranspiration. Now this we can see some kind of example of the shape of the basin which is influencing the hydrograph. See, now here we have a narrow, so peak is touched here, and here it is a broad area, there is no peak. So narrow area always will make you to bring quickly the runoff, and it will make the peak, and when compared to the broad area it is having less peak. And coming to the another aspect, here if you are observing, this is a broad area. So in this particular broad area you can observe there is no peak, but here in a narrow area, so you can see the peak. That means here itself we can understand broad area with respect to the densities, drainage densities, the collection time will take more time to get into that, and it will be less. When comes to the narrow area, it will collect quickly the water, and it will show the peak discharge. And coming to the here, the shape of the basin having two shapes, and you can see here one peak we can expect, and another peak you can expect. Another peak we can expect here. Now the size of the catchment also matters. Either it may be catchment or basin or watershed, whatever it may be. The small catchments behave different from the large ones in terms of relative importance of various phases of runoff phenomena. For example, small catchments always, the small catchments itself defines the area is less, so the collecting of the water will take less time, and it will be gone to overland flow. Overland flow already I discussed in the class types of runoffs, and you can see overland flow is predominant. Even the time base of the hydrographs from larger basins will be larger than those of corresponding hydrographs from a smaller basins. Now the slope also matters in this situation. The slope of the main stream controls the velocity of the flow, obviously. Now here two criteria are there. One is steep, one is flat catchments. So steep catchment, having more runoff, because you can expect this scenario in terms of steep catchment, you can expect this terms of mountain hilly regions. So hilly regions, and flat means like kind of normal regions where there is no much elevation. So you can see the difference here. See, this much peak difference it is showing. That means if a basin is having more steep, it will produce more runoff when comparatively flat catchments. That is what they have mentioned here. And coming to the another one, drainage density. So drainage density, in a simple scenario, the drainage density defines total length of the catchment, total channel length by total area. That means, as I mentioned earlier, if the channel network is more, that means the collection of water will be more, and obviously the runoff will be more. If the collection network is less, then the runoff will be less. That means the best example, channel network is more, is nothing but urban areas, where you can see the urban areas having more impervious surfaces. There you can understand urban areas are not encouraging any kind of infiltration. So they are encouraging more in terms of runoff, that is flood. That's what we can observe. There will be more floods in terms of urban areas, not in rural areas. So here coming to the point, drainage densities, if drainage network is more, means there will be definitely it is situated in urban area and which is having high drainage density, means the peak will be more comparatively less. So here also we can observe lot of difference between drainage density. So drainage density is more means more peaks, less means less peaks. Less itself defines land use, land cover, that means it is dominated by forest area. This fast response is reflected in large peak discharges. So now you understood. So number of networks also matters when we are dealing with respect to the hydrographs. Now another aspect, land use, land cover. So land use, land cover means, for example, initially there are two criteria as shown here, criteria A and criteria B. In criteria A, you can understand there are lot of n number of drainage networks are there, and here drainage network is less. So drainage network is more in terms of A and drainage network is less in terms of B. That means more networks defines more urban area and less network defines forest area. So here itself we can understand the flood hydrographs as mentioned here. More urban area will touch more peak, less urban area and more forest area will touch less hydrographs. That's what, as I mentioned, hydrographs are very crucial in understanding and doing the management perspective of watershed. So if we are able to understand the hydrographs runoffs getting from this particular catchment, then only we can give management techniques. Without understanding these hydrographs, we cannot go for any further management techniques, and we cannot suggest the particular management technique for particular watershed or particular region, maybe sub watersheds. And other climatic factors, as I discussed earlier, it may be rainfall, duration, intensity, storm, directions, and everything will comes into the climatic factors. So this is one of the overall picture of the hydrograph, which is having consisting of the base flow and direct runoff hydrograph. So base flow is nothing but typically the water which is contributed from the groundwater. So from groundwater, that means the water will enter from the surface to infiltration, again further to the percolation, again further to the groundwater. Again it is coming back to the surface in terms of springs, that is called base flow, and it is joining to particular streams, that may be subtributaries, tributaries or main channels. So this is comes under base flow, and some base flow water is in terms of snow also. Snow, melting of the snow will be considered as the base flow. Something water is there without the without that particular event of the rainfall. So now you can see some kind of analysis we can do here. M is the starting, here A is the starting point, and you can see up to A to B there will be a rise, that is called A to B is called rising limb, and P is the peak, that means peak flood flow. This is a maximum flood it can happen for this particular event of the storm. And coming to the section C to D, C to D completely it is with falling limb. That means A to B is treated as rising limb and C to D is treated as falling limb. And here the peak is there, but in between some area which is called B to C, that can be noted as crust segment. So crust segment will plays a crucial role, where it will be divided the rising limb and falling limb, and where we can see the peak discharge, like peak flood for between the B, C and P is the peak flood. So that means you people can understand, first half section is direct runoff hydrograph, second half section is base flow. Yes, so these two things you can remember and you can understand. So now next one we will see important note. So rising limb and crust segments are influenced by storm factors and character catchment factors also. But recession limb or falling limb, which is influenced by only the catchment factors. So these two things are very important to understand. And next one, base flow separation, as I mentioned, this is with respect to the base flow and runoff, and this is with respect to the direct runoff. So both are the different things. And this is the final one, runoff and base flow. So direct runoff is nothing but excluding the base flow. So if you exclude the base flow, then that we can consider it as direct runoff. It is a plot of discharge versus time. Both are with respect to the discharge versus time only. But if we are specifically removing, that means if we are specifically removing base flow from that particular storm, that means our intention is to find how much rain occurred and what is the response for that. It may be the runoff. So without considering the past flow in that particular river, that is nothing but base flow. That is what our concern about base flow. Next, there will be two kinds of problems where we are going to solve. So volume of runoff equal to, if you are taking, for example, the whatever we are considering runoff, always I mentioned this way. Like now we want to discuss about this kind of problems, as well as we have to discuss about this kind of problems to understand the basically how to before going to this major criteria, we need to understand before that a simple problem such that we can able to tackle a complicated things also. So now we are going with the triangular formula as well as the trapezoidal formula. So triangular formula is having half into QP into TB. QP is nothing but the peak discharge where you can see where it is touching. So this is a QP, and this completely duration is called TB. TB means time, base time. QP means peak discharge. Discharge is in terms of Q. So now first problem we can see, a triangular direct runoff hydrograph due to a storm has a time base of 60 hours. So what is the, so first we will go with that thing, 60 hours they are telling, and the peak flow of 30 meter cube per second occurs at 20 hours from the start of the storm, and the area of the catchment is 300. So the basically we will write, so they have given TB equal to 60 hours and peak flow. So when it touched peak flow at 20 hours, it is 30 meter cube per second. And what is the area? Area also they have given. So we have to find rainfall excess. Area is equal to 300 kilometer square. Now we can understand they have given the input data TB, QP and A. You can check that formula. Volume of runoff equal to half into QP into TB. So half into QP into TP. Now you can get what is QP. QP is 30 and TB is 60. So okay, once we will make one small rough diagram there such that you people can understand easily. So this is a base time which is having 60 hours, and this is a peak one, that is QP, which is having 30 meter cube per second. Now 60 into 60. So why we got this 60 into 60? So this is QP in terms of meter square per second, meter cube per second, QP in terms of meter cube per second, but this is only in terms of hours. If you want to get cancel these seconds and hours, you have to convert 1 hour into 60. That means 1 hour equal to 60 into 60 seconds. So that is equal to, so we got some value. Now they are telling to find runoff. So runoff equal to volume by area. That is equal to volume, already we found 1 by 2 into 30 peak discharge into 60 into 60 is the time base, and 60 into 60 is for unit conversion. And coming to the area, they have given 300 kilometer square. That means 300 kilometer square means 1 kilometer equal to 1000 meters. So kilometer square is equal to 300,000 square. Now you can get runoff equal to 0.0108 meters. So you have to convert it into 10.8 mm. So this is the way we have to solve triangular direct runoff hydrographs problems. And similar problem you can understand just changing the values. Please try it by your own. Just I will mention the given data. So TB equal to 90. Okay. Next QP equal to 60 at particular 20 hours, and A is equal to 300. Now you can go directly. So volume equal to runoff equal to volume by area. So what is the formula? 1 by 2 into QP. QP is nothing but QP is 60 into base time is 90 into 60 into 60 is for unit conversion, and 300 into 1000 squares, that is called runoff equal to 39.4 mm. So if you want to make a rough diagram, you can make it like this. Time base is 90 they have given, and peak discharge is 60 meter cube per second. It is touching at the peak. So this is T versus Q. So this way you have to make triangular direct runoff hydrograph problems. In a similar way, just change the value. It is for practice purpose. Just make it a way. So time base equal to 80 hours and QP equal to 200 meter cube per second, and area equal to 1440 kilometer square. And you know runoff equal to volume by area. Volume formula is 1 by 2 into QP into TP by area. Just area you just convert it into kilometer square into meter square. Just put 300 and into 1000 square, then you will get the answer. So next one is also like similar kind. Same, just they have changed the values and you can understand. Similar way, TB is equal to 20, QP is equal to 10, area equal to 10 kilometer square, then runoff equal to volume by area. Volume equal to 1 by 2 into QP into TB by area. Area you just convert it into kilometer square into meter square. You will get the value. And one more thing, another one after the triangular section, there is a one more problem. We can solve it as a trapezoidal section. So trapezoidal it will make TB1, TB2. I'll show you one problem. So a trapezoidal hydrograph has a base time of 70 hours and a rising limb of 4 hours. The peak 4 hours, the peak discharge is observed 90. That means peak they have given QP equal to 90 meter cube per second, and both durations they have given. So here volume equal to area into depth. This is a very fundamental thing. Now they are asking us to find area. So area equal to volume by depth. Depth is nothing but runoff. So volume equal to, what is the trapezoidal formula? So you can check TB1 plus TB2 by 2 into QP. So what is TB1? 74 plus 70 by 2 into, and you have to convert it into hours to seconds and into 90, and they have given clearly runoff is 2 centimeters. Just make a note, assume r equal to 2 centimeters. I forgot to give. Okay, 2 by 100 into 1000 square. So it is already, everything is volume is in meters, like meter cube. Now the runoff is in centimeters. So 100 centimeters equal to 1 meter. Obviously, so 1 centimeter equal to 1 by 100. So 1 centimeter equal to 1 by 100 meters. So now the final answer is 599.4 kilometers square. Okay, we'll see the next problem. So next, another kind of problem we can see now. So initially we have seen triangular, next trapezoidal. Now slowly we are going to combine both the things. You can see here triangular, trapezoidal, trapezoidal, triangular. This is triangle, this is triangle, this is trapezoidal, this is trapezoidal, and this is trapezoidal. That means combination of triangle and trapezoidal only we are going to solve this kind of problems. Now you can see direct runoff hydrograph shows how a watershed responds to rainfall over time. To find the rainfall axis, this volume is divided by the watershed area of 300 kilometers square. So they have given area. Now we have to find individually. Individually in the sense, first we come to know this is triangle, trapezoidal section, trapezoidal section, trapezoidal section, and triangular section. Now triangular section, half into QP into TP. Half into, what is a QP? 10. 10. What is the base? 10. So discharge into 10 into 60 into 60. We will get one kind of value, that is 1,80,000. Next is second volume. Second kind of volume is trapezoidal. So just you have to take another two scenarios here. 10 plus 70 by 2 into, what is the difference? 10 into 10 into 60 into 60. So you will get 144,000,000. And next volume 3, 70 plus, next one, this section trapezoidal, 70 plus 90 by 2 into, what is the difference? 30 minus 20 also 10. So 10 into 60 into 60 into 60. So we will get 288,000,000. Next volume 4. Volume 4 means this section. So trapezoidal, 90 plus 40 by 2 into, here the difference 50 minus 30 equal to 20, right? 50 minus 30 equal to 20. 20 into 60 into 60. So what is the value? 4680000. Another one is volume 5. That is triangular section. Half into, what is the peak discharge? 40. What is the base? 90 minus 50 equal to 40. So here peak is 40, base is 40, and this is 60 into 60. You will get 4680000. Now club it all. That is volume equal to volume 1 plus volume 2 plus volume 3 plus volume 4 plus volume 5. Now total volume is 12.06 into 10 power 6 meter cube. Now depth equal to volume by area. So what is the volume? 12.06 into 10 power 6. What is the area? Area they have mentioned 300 into kilometer square. That means 1000 meter square. So now the final answer is 0.0402 meters. So this is the thing. So like that we have to solve this problem. So it is divided into first triangular section, next second one is trapezoidal, third one is trapezoidal, fourth one is trapezoidal, fifth one is triangular section. So combination of all we have to make it a cumulative and we have to solve it. And one more problem we will see. This is not required. Next concept is unit hydrograph. So what is unit hydrograph? A unit hydrograph is defined as the hydrograph of direct runoff hydrograph. Direct runoff hydrograph resulting from 1 unit of rainfall excess occurring uniform over the basin and at a uniform rate for a specific duration. So that means here they are mentioning 1 unit, like 1 centimeter depth of excess runoff. That means this concept was proposed by Sherman based on the following assumptions. One is time is invariance and linear response. So unit hydrograph is equal to direct runoff hydrograph by rainfall excess. Rainfall excess means 1 centimeter depth. So unit hydrograph equal to direct runoff hydrograph and 1 centimeter depth. Got it? One problem we will see. A 12-hour unit hydrograph, they have mentioned 12 hours unit hydrograph of a catchment is of a triangular shape with a base width of 144 hours and a peak discharge of 22 meter cube per second, and the area is, so they are mentioning some kind of base they have given. So QP equal to 23, TB equal to 144. And unit hydrograph, they are asking unit hydrograph. That means here they need area. So volume equal to area into depth. So area equal to volume by depth. Agree? So volume equal to area into depth. So here we can see volume equal to triangular formula 1 by 2 into 23 into 144 into 60 into 60. It is divided by depth. If they are not mentioning any kind of depth, 1 centimeter depth into 1000 square. So if nothing is mentioning this area, you have to mention 1 centimeter depth. 1 by 100, that is centimeter is converted to meter, that is 100 centimeters equal to 1 meter. So 1 centimeter equal to 1 by 100 meter. That is what here we have converted. And the final value is area is 596.16 kilometers square. So they are asking here 12 hours unit hydrograph of a catchment is of triangular shape with a base width of 144 hours and a peak discharge of 23 meter cube per second. And the area of the catchment is, then they have mentioned. So volume equal to area into depth. So area equal to volume by depth. That is 1 by 2 into 23, that is peak discharge, into 144, that is base width, into 60 into 60. That is for unit conversion. Meter cube per second. So it is in hours base time. So just it is having. So now we can see one more problem. A storm event resulted in a total precipitation of 4.2 centimeters over a watershed. The time of excess rainfall is 2 hours and the phi index is 0.8 centimeters per hour. And the unit hydrograph ordinates for a 2 hours unit hydrograph are given in the table below. So here we can see the table which they have mentioned with respect to time as well as unit hydrograph. So especially they are mentioning this problem is related to unit hydrograph. And determine the peak discharge of the 2 hours direct runoff hydrograph. If the base flow is 7 meter cube per second, find the maximum flood discharge. So first we will note down what are the given data. So precipitation equal to 4.2 centimeters they have given. And what is the phi index? Phi is equal to 0.8 centimeters per hour they have given. And next, is there anything? Yes, T is equal to 2 hours duration they have given. Now we know that pi equal to P minus R by T. So 0.8 equal to 4.2 minus R by 2. Therefore, we will get runoff is 2.6 centimeters. Got it? We got runoff as 2.6 centimeters. And now they have asked two criteria. One is peak direct runoff hydrograph and another one is maximum flood discharge. So peak direct runoff hydrograph means here we can see there is a table with respect to some timings 0 corresponding 0 value unit of 1 corresponding 5 meter cube per second and 2 corresponding 15 and 3 corresponding 12 and 4 corresponding 10 and 5 corresponding 6 and 6 corresponding 0. Now they are clearly mentioning about 2. So 2 corresponding is 15. So 15 into 2.6, that is equal to 39 meter cube per second. That means, see, as I mentioned earlier, unit hydrograph is equal to direct runoff hydrograph by runoff. So if you need direct runoff hydrograph, then R into unit hydrograph. That is what we have written here for this formula. So 115 is unit hydrograph, R is 2.6. And next one, maximum flood discharge, DRH plus base flow. So whenever we are mentioning flood, maximum flood discharge, it should be the combination of direct runoff hydrograph and flood and base flow. So direct runoff hydrograph, already we got 39 meter cube per second plus base flow. What is the base flow they have again? Base flow is 7. They already clearly mentioned base flow is 7. Now 39 plus 7. So we will get 46 meter cube per second is the maximum flood discharge. So this way we have to solve. First they have interconnected phi index. Phi is equal to P minus R by T. So we know the value of P. P is equal to 4.2 centimeters. Phi is equal to 0.8 centimeters per hour and T is equal to 2 hours. And peak DRH is equal to 15 into 2.6. That is nothing but peak DRH equal to unit hydrograph into runoff. So just a multiplying, we need to do multiplying with respect to DRH and runoff. Then the finally maximum flood discharge, that is direct runoff hydrograph plus base flow. What is the direct runoff hydrograph? It was solved with one, that is 39 meter cube per second, as well as the base flow they have already clearly mentioned, that is 7. So totally if we are combining it is 46 meter cube per second. So in a similar way, next problem we will see. A storm resulted in a peak flood hydrograph discharge of 470 meter cube per second with a base flow of 15 meter cube per second. The total rainfall P equal to 8 centimeters and the phi index is 0.25 centimeters per hour over a duration of 6 hours. Now they are asking us to calculate excess rainfall that is R, and determine the peak unit hydrograph originates. Okay, let's solve this problem. First we will write the given data. So P equal to, what is a P? 8 centimeters. Phi equal to 0.25 centimeters per hour. Next one, duration T is equal to 6 hours. So before one I have mentioned flood hydrograph equal to DRH plus base flow. This is very important. And unit hydrograph equal to direct runoff hydrograph by depth. So these two formulas try to remember because we have to find peak unit hydrograph. So now before that we have to calculate phi is equal to P minus R by T. What is pi? 0.25 and P 8 minus R by 6. So R equal to 6.5 centimeters depth we got. Now next one, determine the peak unit hydrograph. Now already we done, one part is runoff, X is runoff. Next unit hydrograph. So unit hydrograph equal to direct runoff hydrograph by runoff. What is DRH? So direct runoff hydrograph they have mentioned 470 minus 15 by 6.5. This is nothing but direct runoff hydrograph equal to flood hydrograph minus base flow. Here we will get 70 meter cube per second. So this is the value for this thing.
Next one, summation curve method, that is also known as S curve. So here the simple formula Q equal to 2.778 into A by D, where A equal to area of catchment in kilometer square and D equal to duration of unit hydrograph in hours. A 6 hours unit hydrograph of a catchment is triangular with a base width of 64 hours and a peak ordinate of 30 meter cube per second. Calculate the equilibrium S curve. So now we need to find Q equal to 2.778 A by D. So D is equal to 6 hours. Area equal to volume by depth. So what is the volume? 1 by 2 into QP. QP is nothing but 30 into 64 into 60 into 60. So 1 by 100, that is what R is, if R is not given in unit hydrograph, so it is mentioned that 1 centimeter depth. Now we can see this is, if they are not mentioning R equal to 1 centimeter. Now you can get the value of area 345.6 kilometers square. So Q equal to 2.778 into 345.6 divided by 6, because unit hydrograph hours they have given in terms of 6 hours. So Q equal to 160 meter cube per second. Now next one, synthetic unit hydrograph, also known as Cinder's unit hydrograph. So basin lag time, some empirical formulas if we are able to know, we can solve this thing. Basin lag time and peak discharge. So you can know here base peak discharge and base type, and width is 50 percentage of the peak and width is 75 percentage of the peak, and duration is D and time of concentration is Tc. So these are the empirical formulas we can substitute directly. So this is one kind of problem. A hydrologist is studying a watershed to estimate its flood hydrograph using Cinder's synthetic unit hydrograph method. The watershed has a longest flow path of 30 kilometers and the distance from the outlet to the centroid is distance to the outlet. That means L equal to 30, LC is equal to 10. Now we can find with empirical formulas, and area is 500 square kilometers and CT is 1, CP is 0.6. Lag time CT into L into LC by 0.3, that is equal to CT is 1 into 30 into 10 all by this. So if you are making 5.54 hours. So next one, peak discharge 2.78 into Cp into A by Tp. So 2.78 into 0.6 into, so we know the area 500, then already we have solved Tp. This is Tp. So Tp is equal to 5.54. So we got 150.6 meter cube per second. So next one, Tb, 3 plus Tp by 8. That is equal to 3 plus 5.4 by 8 equal to 3.69 days. And next one, W50 is nothing but 5.87 into Qp by A whole power minus 1.08. That is equal to 5.87 into, so what is the Qp value? 150 by area 500 . So you will get the answer 21.44 hours. Now next one, W50 by 1.75, that is equal to 21.44 by 1.75, that is equal to 12.25 hours. L by 2 plus Tp. So 30 by 2 plus 5.54. So we'll get 20.54 hours. So these are the just empirical formulas where we can solve it easily. So width of hydrograph at 75% of peak discharge means W50 by 1.7. So first one, lag time is Ct into L into Lc whole power 0.3. That is Ct already they have mentioned 1 and 10 into 30 power 0.3. That is 5.54 hours. And peak discharge is 2.78 into Cp into A by Tp. So 2.78 into Cp is nothing but 0.6 into 500 by 5.54. There is the 150.6 meter cube per second. Next, the base time 3 plus Tp by 8. That is equal to 3 plus Tp means 5.54 by 8, 3.69 days. Width 5.87 into Qp by A whole power minus 1.08. That is equal to 5.87 into 150.67 by area is already they have mentioned, that is 500. Directly you can take it as kilometer square minus 1.08, then you can get 21.44 hours. And finally we are focusing with 75% of peak discharge, where W50 by 1.75 is the empirical formula. Just we have to substitute it in that. So 21.44 by 1.75, that is equal to 12.25 hours. Next, time of concentration is equal to L by 2 plus Tp. What is the L? L already it is mentioned 30 kilometers. That is the longest flow path. So 30 by 2 plus Tp. We have calculated in the first step itself. Tp is equal to the time lag, which is 5.54 hours. Then finally we will get Tc, time of concentration is 20.54 hours. So in a simple sense, if you want to know about the time of concentration, a basic fundamental definition. So there is a watershed. So in a watershed, many like tributaries, sub-tributaries are there. So whatever it may be, so the water is collected from farthest point to the outlet. That means whatever it may be, tributary or sub-tributary, it is having the longest distance. From there the water is collected and it is reached to point, it is called outlet, that is discharge. The distance between the farthest point to the outlet is called time of concentration. That's what we have mentioned in sixth one. So next we can see flood estimation. So as you people know, flood is a natural event where an overflow of water submerges land that is usually dry and often caused by heavy rainfalls, maybe rapid snow melt, or the failure of the water management. So, many empirical methods are there, but few empirical methods which is known are like Dickens methods, Rice method, English method. These are the methods which is used in North India, South India, as well as the Maharashtra and Gujarat. And this is the image where it can be explained clearly. That left side image is focusing normal condition of the river. Whenever we can expect a flood, then it is like this scenario. So this is normal condition and this is flood situation condition. Flood is nothing but excess water is flowing over banks of the river. So excess water which is flowing over the banks of the river is called flood. So just conquering the surrounding area, so that means it is not capable to travel in that particular river and it is exceeding its capacity and coming outside the river boundaries, that is banks, then it is spreading over the surrounding area, that is called flood situation as well as the flood conditions. So one problem we can see on flood estimation: estimate the maximum flood flow for the following catchments by using an appropriate empirical formula. So area is 40.5, like you can consider area is just 40, not 40.5, 40 kilometers square, and CD is 6 and CR is 6.8. Now they are telling Gangetic Plain and Kaveri Delta and Maharashtra. So there are many things are there, empirical formulas. Now we'll go one by one. So Gangetic Plain, if you want to go CD into A power 3 by 4, this is the empirical formula what they have done. And CD value already we know, 6 into 40 whole power 3 by 4. So what is the value? So around 95 meter cube per second. And next one, discharge CD equal to, so CR into A power 2 by 3. What is the CR? 6.8 into 40 area power 2 by 3. So it is around 79 meter cube per second. And in terms of Maharashtra, there is another empirical formula, that is Q equal to 124A by 10.4. So 124 into 40 by 40 plus 10.4, that is equal to 698 meter cube per second. So three different things. We have three different things. Three different empirical formulas are showing three different kinds of results depending on the location of the catchment. Now next one, rational formula. The rational formula is a simple and widely used method for estimating peak discharge. As we know that it's a just empirical formula. Q is equal to 2.78 into CIA. So C is catchment, is like A is catchment area, C is runoff coefficient, and I is rainfall intensity, that is in terms of centimeters per hour. This is one kind of problem. Okay, we'll see this kind of problem. Rather than that, this will be very simple. An engineer is required to design a drainage system for an airport of area 2.5 kilometers square for 35 years return period. the equation of rainfall intensity is I equal to T by T plus 10 whole power 0.38, where I equal to rainfall intensity in centimeters per hour and T is equal to duration in minutes and capital T is return period in year. If the concentration time for the area is estimated as 50 minutes, for what discharge the system must design? So now we can solve. First we'll write given data A equal to A is equal to 2.5 and C is equal to 1. We don't know I. So just I equal to T by T plus 10 whole power 0.38. So I equal to capital T, that is return period. How many years it is mentioned return period? That is 35 by 50 plus 10 whole power 0.38. So I is equal to 7.38 centimeters per hour. So next Q equal to 2.78 into CIA. That is what I have mentioned. This is a rational method. So Q is equal to 2.78 into C. So C means 1 into I. 7.38 into 2.5. So Q equal to 51.29 meter cube per second. So this is the solution for this problem. First they have given area, then we have taken C is equal to 1, then I just substituted the formulas at return period and normal T duration, then we'll get 7.38, then Q equal to 2.78 into 1 into 7.38 into 2.5, that is to 51.29. So one more thing, flood frequency. So flood frequency means the flood frequency method is used to estimate the likelihood of a specific given time period at a particular location. There are several methods for flood frequency analysis, but the most common is Gumbel's method. So I would like to explain this thing, just a concept but not a problem. So just we have to make the probable maximum flood, that is xt plus x bar plus 4k into sigma. So x bar equal to, that is a mean, and sigma is equal to standard deviation, and k is the frequency factor. If you are not able to know, this is a formula where k is equal to yt minus y bar by s bar. There is a frequency factor, y dash and s dash depending on the sample size n, and they are obtained from the Gumbel's table. So for our convenience, they were rewritten the formula frequency factor as k is equal to yt minus 0.577 by 1.2825. If you are able to solve this thing, then we can able to solve yt equal to minus log of 1 minus p. Further, if you want to solve, if you want to know p probability with respect to return period, so p is equal to 1 by t. So this is the way we have to solve the problems. And this is a flood frequency studies used for flood frequency studies. The most common is Gumbel's. So here just we have to know what is the mean, what is the standard deviation, what is the frequency factor, then only we can able to find probability. That means probability is nothing but next the questions means, for example, the questions might be asked like the mean annual flood of a rise in 600 meter cube per second, and they will give some standard deviation and everything. They will ask if it is next within 5 years, whether it is there is a possibility there or not with respect to whether it will reach 600 meter cube per second or 1000 meter cube per second or not. So we have to find the probability whether it will happen or not. So that is the thing. So the next topic is groundwater.
basically, see, we want to revise once again. First, we can see the kind of precipitation. Afterwards, we can see the runoff. Before coming to the runoff, we can see some kind of transpiration, evaporation, evapotranspiration. From there, water will escape with respect to water vapor, that is to the atmosphere with respect to the condensation. Then after condensation, you can see some processes happened in terms of clouds. Again, it will come back as precipitation. And here there is an important thing. Whenever rainfall is happened, there is, we can see groundwater recharge. This groundwater recharge is depends on soil and other factors that we have discussed in infiltration concept, because after infiltration only percolation will happen, after percolation only groundwater recharge will happen. So here, this is one of the major component that we need to understand. The groundwater plays a crucial role in sustainable way. That means we have to encourage more to recharge excess runoff, to recharge, such that after getting recharge in the ground, it will be useful for the future generations. So recharging and extraction, it should be balanced. If we want to talk more, recharge should be happened more rather than extracting the water in terms of ground, because the only source ground, we cannot recharge immediately. It will take long time. So now here they have mentioned groundwater is found in the pores and fractures of soil and rock beneath the earth surface. So here, that means pores and fractures. There is a so-called ground. So this is the ground level. So water need to enter, rainfall need to, after rainfall we can see some kind of water on surface of the ground. So if it want to get into the ground water table, then it should have some gaps like pores as well as some kind of fractures. Then only it will possible. And most of the scenarios, wherever the forest area is there, so if it is dense forest, it will be more water can be recharged to the ground. If it is not there in terms of urban areas, then we have to provide artificial recharge structures such that it will encourage the excess runoff which is going on that particular urban areas. We can make it to transfer it into recharge. Now we can see the another second line what they have mentioned. It originates from the precipitation which infiltrates the ground and moves through permeable layers. So there will be two kinds of layers, permeable and impermeable layers. As we know, impermeable is nothing but it's like a kind of concrete. So there won't be any kind of passage of water from high to low or upper surface to lower surface. It will restrict the water and it will encourage to run off. So groundwater occurrence is very crucial to understand. Now coming to the, slowly we are coming to the types of aquifers. There are two kinds of aquifers, that is unconfined aquifer as well as the confined aquifer. So one is unconfined and confined, which is near to the surface, or else we can tell in other words, which is near to the atmosphere, that is called confined, and unconfined, and which is between two impermeable layers, that is called confined layers. So these are the only two types of aquifers are there. One is confined, another one is unconfined. Unconfined is near to the surface area, and unconfined is between two confining beds. And again, this one also you can see, this also comes under confined aquifer. So now the basic definitions we can see. Unconfined aquifer, an aquifer with a water table that is directly influenced by atmosphere pressure and recharge from surface water. As I mentioned earlier, unconfined is near to the surface and which is exposed to atmosphere.
And for recharging it will take just few hours or few days, or it may take some months or years, you can see here. But when comes to confined aquifer, it will take some decades or centuries or millennia. So it's depending on the things. That's what recharging is very important than extraction. So extraction should be limited, because recharging is very difficult, because it will say take some days, months, years, or decades or centuries. Now coming to the point of confined definition, an aquifer bounded by impermeable layers, that means below the confined aquifer is called below the unconfined aquifer is called confined aquifer. An aquifer bounded by impermeable layers where water is under pressure and not directly influenced by the surface recharge. So as I mentioned, only unconfined aquifer is with respect to atmosphere, and confined aquifer is not with respect to atmosphere. And coming to the water table and its fluctuations, groundwater table and its fluctuations, a very few things here mentioned. One is seasonal changes, another one is recharge and discharge rates. As I mentioned, recharge should be done more compared to discharge. Discharge rate should not be more, because we have to see sustainable way in a future perspective. And geological factors, soil permeability, and another one is tidal effects in coastal areas. These are the important things where it can make fluctuation. Water table fluctuations may happen with respect to seasonal changes, groundwater and discharge rates, and geological factors, as well as tidal effects. Next, coming to another topic, wells and springs. So wells means wells are dug and drilled into the saturated zone to assess the groundwater, which is then pumped for various purposes. That means it's an open well. Wells are just, it will be a shallow depth, and it may be a shallow or a deep depending on the things. Like tube wells also there, which we have to explore more depth to get the water, and normal wells also it is there, where we can get within some limited depth itself, we will get some kind of water depending on the particular area saturation, soil saturation zone, and that river conditions and climatic conditions, and depending on that topographical features of that particular basin, the availability of water and recharge of the groundwater depends. So everywhere we cannot get within the stipulated or exact this down, like exact distance, we cannot get the water immediately. So now coming to the point of springs. Springs is nothing but it is a naturally formed like we can tell it as a naturally formed river. We can make it as springs are natural outlets where groundwater emerges at the surface, often where the water table intersects the land surface. So if we want to make springs in a precise way, we can see here two kinds of images which can discuss about these springs. So here there is a ground. So here recharge has been done. After recharge, again water is coming back. Again it is going to the ground. Again it is coming back. So this coming back point is called spring. So springs is nothing but the water. That means here in a simple sense, this is a ground level, and water went through infiltration, percolation, groundwater table. Again it is coming back to the ground level. That means here it will go n number of purification stages. That means the water which is coming out from springs, mostly it will be pure quality water. So it will be mostly pure quality water. Right side you can see this kind of things. There is no river network But even though the water is traveling from one path to other path, this is only happens because of springs. This you can see in mostly in mountain regions, like any kind of hilly terrains. You can see this is usually occurs because of water holding capacity of that particular hill or kind of mountain. Next, coming to the point, aquifer properties. So first aquifer property, before going to the aquifer property, you can see two terminologies. Here it is newly introduced, porous and permeable. See, porous and permeable. Porous means there is a gaps, like there is a gaps in that particular soil, and permeable means whether that gaps are connected or not. That means, for example, you can see here three different kinds of images where it is indicating. First one is non-porous, non-permeable. That means there is no gaps in this and there is no movement of water, because there is no gap means there is no storage of water. If there is no storage of water, there is no storage, there is no topic regarding flow of water. Next one, porous and permeable. So there is a porous that you can see here. Here some gap is there. Here some gap is there. Here some gap, and here some gaps. So many gaps are there. That means in that gaps the water is filled. Okay, in rainy season mostly. So in these gaps water is filled, but here in this particular water, this is not going to travel from here to here. It is not going. That means they are all locked. They are not traveling from one place to other place in soil. So here we can tell only this scenario is called porous but not permeable. Now coming to the scenario of permeable and porous. So porous and permeable, you can see there are huge number of gaps. Here we can identify there are huge number of gaps, and that is called porous. And coming to the permeable, that gaps are allowing water to travel from one place to other place. Here you can understand. So water is traveling from one place to other place. That means that gaps are allowing water to travel from one place to other place, from upper surface to lower surface. This is called permeable. That is called permeability. Now the definitions you can see, porosity is nothing but the percentage of void space in a material compared to its total volume, and permeability is nothing but it's traveling from one place to other place. That is the ability of an aquifer to transmit water through its pore space or fractures. As I mentioned, pores or fractures are similar. There is some gap. With that gap, it is connecting each water, and it is traveling from top to bottom. Bottom is nothing but groundwater. Now coming to the two scenarios, you can see here two images. The left side image, which is encouraging water to travel from top to bottom, that is high permeability are there, because here the soil particles diameters and the diameter is having huge, so there won't be any kind of, there will be more space is there. And coming to this side, soil having like it is very small in terms of dia of the soil, and here you can observe it is allowing obviously, but with the less rate it is allowing. Here it is allowing, but it is allowing very quick rate. So allowing water quickly is required rather than allowing water in a low permeability. That is two kinds of aquifer properties. Now Darcy's law. So Darcy's law is nothing but, as I mentioned, there are pores as well as there are permeability. So permeability is nothing but the flow path which connects all the pores. So that is derived by Darcy's law. In a simple sense, Q equal to KIA. So Q equal to KIA. What is Q? Discharge. K is hydraulic conductivity and I is hydraulic gradient and A is cross sectional area. Now coming to the another kind of properties in terms of aquifer, specific yield and specific retention. So now it is interconnected with porosity. You can see porosity if you taken as n. So what is specific yield and specific retention? So yield means the water which is removed from that particular area, or specific retention means the water which is retained in that particular area. So when we are going with porosity, porosity is nothing but gap. In that particular gap, whether water is removed or whether water is retained, both things are required, because porosity defines just there is a gap, whether it is occupied with respect to water or not, it doesn't mean. But porosity defines it's a combination of yield and retention. So both things should be there, that is n is equal to specific yield plus specific retention. Next, there will be another two kinds of properties, transmissivity and storage coefficient. Transmissivity means something it is passing, the ability of an aquifer to transmit water across its entire saturated thickness, and storage coefficient is the amount of water released or stored per unit area per unit change in hydraulic head. So one small problem we can discuss. A confined aquifer having following characteristics: thickness B equal to 30 meters, hydraulic conductivity K is equal to 8 meter per day, and specific storage equal to 0.0003 per meter, and hydraulic gradient equal to 0.01, and cross sectional area 100 meter square, and porosity is 25%. So porosity equal to specific yield and specific retention, the combination, and specific retention is 10%. Now they have asked multiple questions. First one, compute the transmissivity of the aquifer, and second one, calculate the storage coefficient of the aquifer, and third one, determine the discharge using Darcy's law, and fourth one, find the specific yield of the aquifer. So now compute the transmissivity of aquifer we will solve. So first one, transmissivity T is equal to K into B. This is a standard formula. What is K? 8 into 30, that is equal to 240 meter square per day. And next one, storage coefficient of the aquifer, SS into B. So what is SS? SS is nothing but 0.0003 into B is 30. So you will get value of 0.009. So what is the value of this? Is standard formulas, please try to remember it. Third one, determine the discharge using Darcy's law. So what is the Darcy's law? Q equal to KIA K into DH by DL into A. So what is K? K value is 8 into 100 into 0.01. So you will get discharge in terms of 8 meter cube per day. And final one, they need fourth one, that is porosity. As I mentioned, N is equal to SY plus SR, specific retention and specific yield. The combination of both things is called porosity, and in that specific yield you can find with respect to N minus SR, where N is equal to 25 minus 10, that is equal to 15%. So this way we have to calculate computer transmissivity of the aquifer T is equal to K into B, and calculate the storage coefficient of the aquifer S is equal to SS into B. Then next one, determine the discharge using Darcy's law, that is Q equal to KIA. Again, I is DH by DL, that means hydraulic gradient. And next one is specific yield of the aquifer. And next we'll see one more problem. So a groundwater reservoir is experiencing a decline in the water table due to the extraction. Given the following data, determine the volume of water lost from the aquifer. So here they have given porosity, specific yield and change in groundwater table and area of the aquifer. So very good. We got the required data and we will see the volume of water lost. Volume of water lost is equal to SY into volume. So what is the value of SY? Specific yield 0.2 into volume. What is the value? Volume in terms of kilometers? 100 kilometers into kilometer square, just convert it into meters. 1000 meter square into 0.25. So here you will get 5 into 10 power 6 meter cube. That is a volume of water lost. That is what required for us. Volume of water lost.
So one more session we will discuss regarding irrigation. So irrigation. Here we can see one kind of thing, how plants transport water. Some water we can see in soil, right? Like soil moisture. So from here it will collect the water through roots, and from roots it will travel to stem, and from there it will travel to entire part of the plant, and from there it will reach to leaves. From there, with the openings of tomato, it will make transpiration. Here we can see water and minerals are absorbed by roots. Through the use of capillary action, the xylem pull water and minerals of the stem to leaves. The next step is water and minerals are transported to leaves by the xylem and photosynthesis occurs. And next one, small amount of water evaporates through stomata. Can see here irrigation engineering in a simple words. So irrigation systems, this is a upper stream and this is a downstream, and here we call it as dam, a weir or barrage. So anything we can call, like it may be dam construction or weir construction or barrage construction. Just we are diverting the water from here, from main stream to this side, and this main channel, from main channel again it is diverted to the branch channel. From branch channel again it is diverted to major distribution. From major distribution again it diverted to minor distribution. From minor distribution again it is distributed to field channels. From field channels it went to command area. This command area, gross command area, and this all things culturable command area I will discuss in upcoming problems, such that you people can understand very easily. And here you can see head regulator, that is used for branch channel BC, and cross regulator is used for main channel. Okay, here you can see. So now the science which deals with artificial science of water to the crops is called irrigation engineering. That means the amount of water we got. So the science which deals with the artificial supply of water to the crops is called irrigation engineering. Irrigation system comprises of hydraulic structures like dams, weirs, and barrages, and more. engineering. Now, here it is presented three types: saturation, field capacity, as well as permanent wilting point. So all saturation means nothing but, as I discussed in earlier classes, there will be kind of small spaces or gaps, that is pores. In that pores, if water is passed, that is called permeability, right? So in a similar way, here there are small gaps. That gaps are filled with water. So that is nothing but, completely it is filled with water is nothing but saturation. Now coming to the field capacity, here you see the water in large pores has drained. That means here white color you are observing, right? That means blue color indicates water, white color indicates it is removed, water is removed from that pores. So here completely in this scenario it is water is completely there, and this scenario some water and some water is retained, some water is yielded and some water is retained. And coming to the point, permanent wilting point, water can no longer extract water. Here you can see, when compared with field capacity and permanent wilting point, you can see here the huge difference. Here only few white, that means yield is there, but here it is huge yield. That means we can, it here in this point, third figure, it cannot be, water cannot be extracted. So that is the thing, water cannot be extracted in permanent wilting point. Next, coming to the available water, there are three types: hygroscopic water, capillary water, gravitational water. So now considering first one, gravitational water with respect to saturated, with respect to saturated. So that means here you can see these are the soil particles, and blue color indicates completely the surrounding is filled with water. Then capillary water, little amount of water is lost. And coming to the hygroscopic, soil particle is surrounded by little amount of water. Here you can see, but majority of the gaps are there. In that gaps, yield is there. It is not retained the water, only very limited water is retained. And that's what, as I mentioned in earlier figure, from this onwards we call it as permanent wilting point. You can see, as I mentioned, plants can no longer extract water. So this is the thing, plants cannot no longer extract the water. Plant available water, that is field capacity. So up to here plants can take the water, but and this part it cannot take the water. Now next, coming to the types of irrigation systems. Surface irrigation, subsurface irrigation, drip irrigation, sprinkler irrigation. Surface irrigation means water is distributed over the soil surface by gravity. That is called surface irrigation. Water is distributed over the soil surface by gravity. And subsurface irrigation, water is applied below the soil surface through the underground canals or pipelines. So two types you can see here, one is surface, one is subsurface. So surface is nothing but water is distributed over the soil surface by gravity. Subsurface is nothing, water is applied below the soil surface through the channels or pipelines. And drip irrigation, water is delivered directly to the root zone of plants in small, precise quantities. And last one is sprinkler irrigation. Water is sprayed over crops, simulating natural rainfall. Natural rainfall. So water is sprayed over crops, simulating the natural rainfall. So these are the types of irrigation systems: surface irrigation, subsurface irrigation, as well as the drip irrigation and sprinkler irrigation. There are many types which are related to these things, but these are the most important things, because surface and subsurface will cover everything. In that particularly we can see the drip and sprinkler irrigation. Method of application: free flooding. That means water flows freely over the field without specific control structures, suitable for irregular terrains. That means, so water flows freely over the field without specific control. That means there is here free itself defines without specific control, suitable for irregular terrains. And another one is furrowing method. Water flows in a parallel trenches rows of crops. And next one is ring basin method. So ring basin method means, water is applied in a circular basin around trees or plants. So here are the images. So here the right side is some images they have mentioned clearly regarding. Now you can see crop seasons. So Kharif season and Rabi season. So Kharif season means June to September. That means majorly it is focused with respect to rice, maize and millets. In other terms, bajra and jowar. And Rabi season, it is between October and November, but it is majorly focused wheat, barley and gram and chickpeas. So this will comes under monsoon. So this will comes under monsoon, and this will comes under post monsoon. So here in Kharif season, more water is required when compared to Rabi season, less water. So whatever the rainfall occurred here, we will be like stored in terms of dams, and that will be utilized here for this cultivation of the crops. Now crop water management. The crop water management is the total amount of water a crop needed for growth, development and yield. So crop needs for growth as well as development and yield. It depends on factors like many factors. We can see climate, soil, crop type and growth stage and rainfall. That means, for example, if climate is not in a good way, it is not reacting in a good way, so we cannot get, for example, you can see some rain may happen in terms of summer season, so it is very big effect for mango cultivations. So in the way, when we are doing any kind of crop, it doesn't mean that not only depending on the crop growth and stage and everything, it depends on the climate. If any in between any cyclone happen, because of cyclone we will get like kind of heavy rains. So it may destroy. So depending on the factors, depending on crop outcome, majorly depending on climatic conditions, that means climate change scenario, and what is the soil and what is the amount of nutrients it is having, and crop type. And coming to the crop type means what crop you are going to farm, and what you will get the outcome, and how much extent that particular land will bear, and growth. So whether it will having any kind of growth, decay, or like it may be good growth or it may be bad, like not a good outcome. Growth is nothing but in terms of outcomes of production. And rainfall, you have to be aware of rainfall depending on your crop pattern. So if your crop is well suited for rainfall, then it is okay. If it is not, then you should not go with that thing. So that's what everything will be depending on growth, development, as well as the yield. Yield is nothing but the outcome. Now you can see here three classifications where water is required more. High water is required for rice as well as sugarcane, and moderate water is required for wheat as well as maize. That means in a simple terms we can call it as a corn. And low water requirement like oil seeds, that is groundnut and sunflower. So now you can understand, depending on the crop, you have to choose the season, and you have to go with the kind of water management things. So high water, moderate water, and low water requirements. Now coming to the point, duty and delta. So duty is nothing but how much land can be irrigated with 1 cumex of water. Now you can see it is in terms of this cumex, meter cube per second, generally expressed in hectares per cumex. So that is how much land can be irrigated with 1 cumex of water. So that is the thing. Cumex means meter cube per second. Now duty is nothing but area by discharge. So delta is the total depth of water required to grow a crop for planting to harvesting. So now it is a total depth of water required. That means how much depth of water is required to grow a plant for harvesting, and how much water does the crop needed over a season. So entire season, how much water is required, how much depth we have to maintain, and for 1 cubic of water, and how much land can be irrigated. So both are important things. Derive the relationship between duty and delta. So it is a simple empirical formula, 8.64 into B by delta. And always you keep it in mind that D should be in hectares per cumex, and B is in base period in days, that is number of days the crop needs water, and delta in meters. And factors affecting the duty: type of soil, type of crop, and depending on the soil, depending on the crop, depending on the slope of the ground and climatic conditions, method of application of water, and type and location of canal, and base period of the crop, and soil contents. So type of soil one, type of crop is another one, and slope of the ground, climatic conditions, and method of application of water, and type and location of canals. So now soil is plays a major role as well as a crop, as well as a slope, as well as a climatic conditions. Now we can see some kind of problems in this unit. Find the delta for a crop when its duty is 432. So what is the 432 hectares per cumex on the field if the base of the crop is 150 days? So the delta they have given, delta means duty they have given. Duty is B is equal to 432. Sorry, this is D. D is equal to 432 and B is equal to 150. Now there is a simple empirical formula, delta is equal to 8.64 into 150 by 432. So delta is equal to 3 meters. (300 centimeters). Given that the particular crop requires about 20 centimeters depth of water at an interval of 40 days and the base period is 400 days, find the delta for the crop. Now using this delta, find the duty of the crop of water for the crop. So now what they have given, just try note it down. First they have given, so here we have to find number of irrigations, that is equal to base period, that is equal to 400 by 40, that is equal to 10, right? Base period they have given 400 and this is 40, that is equal to 10. Number of irrigations is 10. So now you can go delta is equal to, what is the, so now 10 number of irrigations into depth is, that is depth is 0.2, that is equal to delta is equal to 2 meters. And next one, a canal carrying discharge of 20 cumex has a culturable command area of 20,000 hectares with the intensity of rabi crop of 80% and base period of 120 days. So 80 by 100 into 80 by 100 into 20,000, that is 16,000. So duty equal to area by discharge. That is equal to area is 16,000 by discharge is 20, that is equal to 800 hectares per cumex. So here culturable command area is nothing but you have to take only like whatever the percentage they are asking. In another example you can see gross command area and culturable command area, but here area has given 50,000. So here culturable command, only culturable command area means what is the irrigated area. So now you can take 80% into 50,000 CCA. So that is equal to 40,000 hectares. Next Rabi season they are asking 60%. 60 by 100 into 40,000, that is equal to 24,000 hectares. So Kharif season is 24,000 by into 20 by 100. Now you can get Kharif season as 10,000 hectares. Now crop ratio you will get 24,000 by 8,000. So this is what the required thing. So now next topic is reservoirs. We'll see the reservoirs. So a reservoir is a man-made or a natural storage area for water. That means when we are constructing a kind of obstruction across a river, that means it may be a dam or it may be a barrage or anything, some kind of water we can able to store. So if you are taking dam, so this part is called reservoir. So it may be a man-made or a natural storage area for water, typically created by constructing a dam across a river or by modifying a natural lake. So it is used for various purposes such as irrigation, drinking water. So obviously it is used for the irrigation, domestic, drinking water, and other things, hydroelectric powers, and as well as the flood controls and recreation. So now we can able to see reservoir is having more important. That means in terms of when we are getting monsoon rainfall, so definitely we have to use that kind of water. If we are not using by storing it, first we have to store it, then we have to use it for agriculture or sorry, like a domestic purpose or industry purpose, we can use it. So it's purely depending on monsoon. So for such that criterias, so we have to go for some constructions of the dams and we have to fulfill it. So before going to the dams, like if you want to construct a dam, then there will be a thing called some kind of things we have to take care. First, site selection. So now the first one is called site selection. So most important, we have to choose a proper site such that it should store more water and it should be useful for irrigation, domestic as well as the industry purpose. That means storing more water is not only the agenda, but we have to see the losses in terms of infiltration losses, like we call it as seepage losses from that particular dam. So it should not have any kind of seepage. That means here dam is there, so this water should not go from here to here after storing, though it really comes under the losses. Next, before selecting the site location, we have to consider the hydrological perspectives analysis. Hydrological perspective analysis is one of the major important. See how much rainfall occurred in that particular area and what is the runoff is happening in that particular watershed, and what is the losses, whether the losses are more or less in terms of evaporation, transpiration, evapotranspiration, and in terms of infiltration, recharging, and what is the climatic conditions in that particular watershed, whether it is a harsh or it will be a good, depending on that what is the future scenario and the future scope of the that particular basin when it is reacting with the maximum flood events. So whether this can be this particular place can be withholds the water or not. So everything will comes into the picture. Now one more thing is sedimentation. So sedimentation I will explain in the next upcoming slides. So sedimentation always is a challenging aspect in controlling the or producing the water or storing the water in that particular dam, because all the sediments which are coming from the entire dam, entire watershed will store here. If it is completely sedimented like this, then there won't be any kind of storage. So we have to take care of the sedimentation analysis also. It will be very good to understand. And coming to the environmental aspects, environmental aspects means so environmental aspects means we have to consider whether if we are making environmental social economic impact means if we want to construct at one particular location, this particular location is good for reservoir means, then you have to think about what is the sensitive plants, sensitive species, and like animals which are going to affect in that particular area. We have to take care. So depending on that, we have to see which are going to affect, and we have to relocate in a perfect environment, other similar environment, and we there should be less displacement of like people whoever staying in that surrounding area. There should be, if it is less displacement from one place to other, it will be good. If it is more displacement, it is not economical also. So cost will be more, and displacement is not because some people may be addicted for that particular environment, may not be good in terms of going to other area. So socio-economic impact plays a crucial role. And structural and design feasibilities. Structural means the dam, whatever we are constructing, the type of the dam, we need to take care. What kind of structure and what is the budget, depending on that we have to on that particular area, we have to do analysis. And design feasibility, whether it is feasible or not, because whatever the dam we are constructing, so we have to be taking care of the surrounding naturally available materials. If it is there, it is well and good. If it is not there, it will be transportation charge, and everything will be increases the cost of dam construction and reservoir maintenance, and everything will be more. So if it is naturally available materials are there nearby the dam, it will be very good for any kind of construction of the dam. So reservoir investigation not only stick with these 3 or 4 points, but there are many a number of points which we have to go through the narrow down. That means precisely we have to think about it. So site selection, one of the major thing. Another one is hydrological and sedimentation analysis, and environmental impact, as well as the socio-economic impact, and structural and design feasibility. So these all things we have to be taking care. So reservoir investigations. Now coming to the site selection. Site selection. Now coming to the site selection, large catchment area. That means we have to select the large catchment area when compared to the small catchment area. That means we can store more water. So then storing, because our ultimate agenda is to, we have to store more water for irrigation, domestic and industries. So area should be large area and minimal seepage. As I mentioned, the seepage, whatever the dam, so from here to here, seepage should be minimal. And stable geology and strong foundation. So stable geology and strong foundation. And considerable accessibility and proximity to water divine and areas. As I mentioned earlier, if we are constructing any kind of dam or reservoir, whatever the stored water need to be supplied to irrigation sector or domestic sector or industry sector. So these three sectors, if we want to transport from one location to other location. So we need to be precise in terms of it should be near located, it should not be more. So if it is more far away, the cost of maintenance and transportation and everything will be leading to the more. So that is what, considering the accessibility and proximity to water demand areas and minimize displacement of people. As I mentioned, we cannot displace major settled people, because if it is that way, the cost and the people who are stayed in that particular location, when they are shifting from one place to other place, they won't, they will get disturbed. They might get the displacement, but they will miss that environment, perfect environment whatever they were lived previously. So minimum displacement is okay, and minimum environmental damage is okay. Environmental damage minimum means, in the sense, if some particular species are there, so we can shift to same environment in other locations, and we can safeguard them. Like how we are shifting the people from one location to other location and providing everything, in the same way it should be, everything will be minimum. See, without disturbing minimum, there won't be any kind of progress of work. So there will be, definitely there will be some kind of minimum displacements will be there. So in that aspects, so minimum displacement of people or minimum environmental damage, and we have to consider some minimum seepage, even seepage also we are considering minimum. So it will be there, every aspect there will be minimum. So now the classification of rivers. Now classification of rivers based on the purpose. So first, what purpose we are going to construct a dam, or construct a dam for storing the water for the purpose of things. Only it is for storage, or it is for flood control, or it is for multi control. That means whenever we are going to consider, we want to make a reservoir, so we should have a prior knowledge regarding that. Depending on that, we have to go for further things like storage, flood control, multi-purpose. And coming to the, based on storage periods, one will be perennial and seasonal. See, perennial making a dams or reservoirs is very challenging when compared to seasonal. Seasonal means only you can see the kind of season means June to September. You can see some kind of rainfall and you can have some disturbance in the work. But when comes to the other seasons like winter, summer, we can make any kind of constructions in a easy way. So when we are going with perennial river, it will be we can do, but it will be more intense and time taking. And coming to the, based on the hydraulic design, the hydraulic modeling and analysis. Before going to the purpose of any kind of purpose, storage, flood control, or multi-purpose, we need to do some kind of analysis. Hydraulic modeling, modeling analysis, we need to do hydraulic and hydrological modeling analysis. We need to be done, and environmental and ecological considerations. So we have to understand what is the impact of environment in that particular area, and how it is going to impact, and ecological consideration. These all things we should know before going into the. Now storage zones. Dead storage and active storage and flood storage, surcharge storage. So dead storage, so the water at the bottom that cannot be used due to sedimentation. That is called dead storage. I will show in a image also, then you people will can understand easily. Simple to remember. The water at the bottom that cannot be used due to sedimentation accumulation and active storage. Useful water, that is the volume of water available for using between minimal and normal pool. That means here we can use the water for any kind of purpose. It may be irrigation, domestic or hydroelectric powers. And coming to the flood control storage, the space reserved to temporarily store flood water, preventing downstream flooding. This is very very important. So we have to be aware of this thing, preventing downstream flooding. So the space reserved to temporarily store flood water, preventing downstream floods. That is majorly used for flood control storage and surcharge storage. The extra capacity above the flood control level used only during extreme floods before water spills over spillways. So first one is bottom part is dead storage and second part is useful storage and third part is flood control storage, that is preventing the downstream flooding, and fourth one is final one is surcharge storage during extreme floods before water spills over the spillway. And this is the diagram. Dead storage, sediment accumulation. You can see at the bottom of the dam, sediment accumulation, dead storage. Minimum pool and normal pool. This space is between active storage or useful storage. That is, it can be used for any purpose. But dead storage, as I mentioned, sediment accumulation is a major thing. So if more sedimentation is there, it will be problem for the dam. And flood control is nothing but it is for, as I mentioned, for preventing the downstream. And surcharge is nothing but it is for extreme floods. This is a spillways. You can see this is a dam. Sluice way. And safe field is nothing but the maximum amount of water that can be supplied without depleting the storage. So safe field nothing but maximum amount of water that can be supplied without, that means you have safe field, you have to supply the water, but you have to be taken care with respect to, yeah, like minimum you have to maintain and you have to supply it. Depends on inflow, because safe field is depending on the how much water is getting and how much is getting evaporated and what are the supplies we have done. It may be irrigation, domestic, or else other kind of things. Ensure sustainability of reservoirs operation over dry periods. So ensuring the sustainability of the reservoir operation over dry periods also. So dry periods in the sense, so summer in summer you can see it should be able to it should have the capability to provide water for the needs. So we cannot extract whatever the stored water in rainy season. Immediately we cannot supply it back to the needs immediately, and we cannot empty it. Requires long term hydrological data analysis. So to understand this we need long term data. So reservoir sedimentation means, before going to this concept, I want to clarify one thing. See, now this is reservoir sedimentation. See, reservoir sedimentation means, before going to understand, you people need to understand what is soil erosion, what is sediment yield. If you are able to understand this causes and effects, we can make it in a simple way. So soil erosion is nothing but, for example, here you can see a kind of mountain is located in this watershed. So here the soil is eroded. The soil is eroded and deposited here. Again the soil is eroded and deposited here. Again soil is eroded and deposited here. That means within the catchment, if the soil is eroded and deposited, that is called soil erosion. If it is extending its limits and passing through some network of river and coming like this and connecting and going out at the outlet, that means the entire sediments were transported from the watershed to the outlet, that is called sediment yield. So causes means, what is the cause? First cause is soil erosion. Obviously if soil erosion is further shifted from mountain regions to flat region, again from undulated, from here, if it is shifted from one location to another location, and if it is reached to outlet, then obviously we can see the kind of sedimentation. So soil erosion is one of the triggering point for sedimentation, and that for soil to get soil erosion, the another point is the deforestation. If deforestation is happened, soil erosion will happen. So high river sediment loads during floods. So now the effects: reduces reservoir storage. Obviously if everything is coming and settled down, so this bottom part, so this bottom part is sediments. That means if this soil erosion is triggered, soil erosion, soil erosion, and soil erosion, and soil erosion. If soil erosion is converted to sediment yield, then we can understand the concept that it is continuously remove the particles from that particular watershed, and it is letting out from the watershed. That count, if it is more, and if it is coming and depositing in this water, in this dam reservoir, if it is completely deposited, then it will be very difficult to maintain. So reduces the reservoir capacity storage, because obviously if you take something, you call it as a container, and you imagine you just poured 1 liter of water, and the same container you take, and before pouring 1 liter of water, just imagine you have dumped some kind of soil in it, and you see, now you see, if you pour 1 liter of water, it will be like this. You see, this is 1 liter. Obviously this is also 1 liter, but what is the thing happened here? Because here we are incorporated sediments. So if sediments is more, reduces storage capacity. That means, for example, if you put another 1 liter of water here, you can store another up to another 500 ml of water, but here you cannot store 500 ml. Here maximum you can store 250 ml of water. That means remaining 250 ml of water is lost. So it is lost. That means Here, initially, if the sedimentation is less, only few sedimentations are there, then you can store up to 1.5 liter of water in a simple sense. But here you are able to store only 1.25 liters, but another 0.25 liters lost in terms of, because addition you have added sediments. So that is a major thing, major difference you can understand here. So now another one is increases maintenance cost. So it increases maintenance cost, because obviously if continuously if you are able to, if you are not able to properly do analysis with respect to soil erosion, deforestation, as well as rainfall and runoff analysis, and the climatic conditions, and finally coming to the sedimentation yield, then everything will be stored on the bottom of the reservoir, and it will increase, decreases the storage capacity, and increases the maintenance cost. We have to remove that, so it will increase the maintenance cost, like more maintenance cost it will be happen. Now the coming to the point, another point, water quality as well as aquatic ecosystems, we have to be taken care in that particular reservoir, what is the quality of water, and we have to maintain it, as well as aquatic ecosystems. So both things we need to be precise. So now coming to the sedimentation controls. Sedimentation control measures, now you people can understand, one is structural, another one is non-structural. Why structural measure means, check so like we have to provide check dams. Here you can see the image right side bottom, this is a check dam. That means in that particular watershed, for example, if you are considering this is a watershed, for example here you have located a dam. So this is the dam, such that if you are coming that you are storing this entire watershed dam, that means you have you if you want to control sedimentation, just construct here one check dam, and here one check dam, here one check dam, and 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 here one check dam. That means if you construct multiple check dams, you can reduce the load of sediment yields which is going to store in the main dam. You can reduce heat by increasing check dams. So if you increase the check dams, obviously you will reduce the load on the main dam. Next, gabion structures. Gabion structures means you can, this is a kind of, this is also kind of check dams, but it is protected with respect to the mesh. And retaining walls, obviously if you are not providing the good retaining walls, here the soil erosion may happen and it will convert to the sediment yield, then it will go away, wash away. And non-structural measures, land use planning. So that means if we are encouraging, as I mentioned, deforestation, if we are encouraging deforestation, it is directly impacting soil erosion as well as the sedimentation yield. That means if we are encouraging afforestation, then obviously if you are encouraging afforestation, then we can reduce the soil erosion, we can reduce the sediment yield. If you are encouraging deforestation, this is, it comes to the adverse effects in terms of, so sedimentation and soil erosion. That's what we should not encourage, deforestation, and we have to encourage afforestation. So now proper drainage managements need to be provided. The best example is retaining wall structure, the proper drainage measurements. And there should be, there won't be any kind that not only doing the technical things, but also it should be given to the public awareness. Public awareness participation is very important, because they should know what we are losing in terms of, for example, if more sedimentation yield is coming and storing in that particular dam and reservoir capacity is reduced, then we can, they cannot provide any kind of water for irrigation and domestic as well as industries. Then it will be affected directly or indirectly with respect to the public. So they should have the awareness regarding these things. And training programs need to be conducted and need to be implemented in a not this much big check dams. It will be a small kind of check dams. We can use it for third order streams also, or you can use third order streams minimum, or else like you can make a check dams. Now coming to the dam. So finally we came with across with the reservoir. Now dam. A dam is a structure built across a river or a stream to store water. Obviously to store, to control. To control means flood. To regulate water flood, various purposes, sorry, irrigation, domestic and industry sectors, and more sectors also there. And a dam collects water from precipitation and runoff, storing it in a reservoir. Some of this water evaporates or infiltrates into the ground, recharging the groundwater. The dam releases water in a controlled manner for irrigation. The dam releases water in a controlled manner for irrigation, hydropower, and maintaining the river flow. So, depending on dam, also same similar kind, it depends purely on with respect to particular climatic condition and what is the rainfall and what is the capacity and what is the storage and everything, it depends. Now the purpose of the dam, to store the water, to give the hydroelectric power generation, and to control the flood, to make it irrigation, to make a navigation, recreation and tourism, environment and wildlife conservation. So these all things. So not only to purpose of store, flood control, irrigation, as well as the navigation and recreation and tourism is also important, and environment and wildlife conservations and hydroelectric power generation. Now the purpose of the dam, so you people can understand easily. Yeah, thank you. We'll see in next lectures. So the next topic is water resources engineering. So after understanding brief description regarding precipitation, runoff, and infiltration, percolation, groundwater, then understanding about transpiration, evaporation, evapotranspiration, next understanding about water vapor and condensation, and you can get it back again in clouds, you can see again precipitation. This is called cycle. So if you are able to understand this cycle in a precise way, so we can do management. As I mentioned, there are multiple things we have learned, new terminologies in this ongoing session, like sediment yield, soil erosion, and irrigation, and runoff, infiltration in that hot turns, and phi index, w index, and coming to the transpiration, evaporation, evapotranspiration, and coming to the runoff, hydrographs, and groundwater, and groundwater recharge, groundwater tables and springs, wells, everything. So now after understanding all the things regarding the cycle, and for particular basin, if we want to do any kind of remedial measures, meter cube per second, so these all are required. Now another aspect is called water resources engineering. Now how we are going to manage the water in a precise way. That is what most important. That means managing water in a precise way is required. So that is what first managing water resources engineering is nothing but managing the water. Now you can see the role of water in national development. So the role of water in national development, you can see it is most important in terms of water resources in agriculture sector. So any country, it is required agriculture. Next industries, next domestic sectors to share water, to distribute the water. So agriculture is a major thing anywhere, particularly like India country, agriculture is more dependent. So for that purpose, the role of water in national development is importance of water resources in agriculture, industries as well as the domestic sectors. Not only this, there are many things which will be most important like socio-economic impacts. Like for example, if we are distributing water only in monsoon season, we can see kind of agriculture. But if we are able to make a dam and we can store the water, then if we are distributing to other season, then we will get instead of one crop, we will get another crop. That means instead of one crop, we will get another crop means we will get two crops. That itself defines we are increasing the economy. That means we are increasing the economy of particular farmers, and it's a circular thing. So like that. So that means we have to take care. That means if we are constructing dam, we can remove the water scarcity and surplus water is used for other purposes. So water as a driver for sustainable development. So sustainable development means in a simple sense, for example, today we have 10 liters of water. So we should not use all 10 liters of water by today. We have to store it at least 5 liters of water for our future generation in a simple words. So this is called sustainable development. We have to utilize, but we should not utilize everything, but we have to store it for future because they have to live, they have to survive. So we have to utilize the water and but we have to store it a time. So sustainable development need to be done in many sectors. And next one, assessment of water resources. Surface water assessment, groundwater assessment, data collection method. So surface water assessment is nothing but the best example rainfall runoff methods. In a simple way, what is the rainfall? That we can read it as P for no confusion, precipitation. And what is the runoff in that particular catchment? Just if we are able to know this relation with respect to losses, then we can go with good assessment in terms of surface water assessment. There is a many kinds of softwares which can be done. Is one of the best software tool is SWAT, soil water and assessment tool, and HEC HMS and Mike Shea. And now you can be it can be like you can use here like these three for a good results. So most of the researchers are using this thing because of the this is belong to semi distributed physical processing model. Now coming to the groundwater assessment, that is recharge aquifer characteristics. Depending on the recharge and aquifer process and data collection methods, hydrological surveys, and now advanced things like remote sensing methods are more. So data collection methods includes hydrological surveys and remote sensing. So assessment of water resources. So that means here one surface, one groundwater, one interaction of surface and groundwater. But everything wherever we are going to deal, either it may be ground or surface or interaction, the data collection is very much important. For an instant, if we want to do rainfall runoff modeling, for example, in particular SWAT model, the input data is like in terms of we need rainfall, we need minimum temperature, we need maximum temperature, and we need solar radiation, we need relative humidity, and we need wind speed. These are the input variables which are required for SWAT, and another physically input variables are land use, land cover, and soil, and digital elevation model. That means in digital elevation model is nothing but slope. So these three things are required, and along with this output is also required. What is the target? It may be multiple targets depending on your criteria. You can go here. If you are rainfall runoff model, mostly it will be discharge is the output target variable. So this we will do in SWAT cup. In SWAT cup, with respect to calibration and validation, we will do this kind of analysis. Okay. So there will be huge hectic work to understand surface water assessment. Even one surface water assessment, we are dealing with one model called SWAT. So there will be, as I mentioned, there will be many kinds like HMS, Mike Shee, and Mike 11, and these all things are there to understand. Like groundwater means mod flow. Like combination is also there, and top model like kind of things. Depending on the situation, we need to be assess the water in a precise way, and for that we can give some kind of suggestions. Now planning process. The planning process involves the stage of water resources planning. That means pre-feasibility we have to see, next feasibility we have to see, and detailed project report we have to see. So planning processes involve stage of water resources planning, pre-feasibility, feasibility, detailed project report. Next, coming to the other one, stakeholders involvement and participation approaches, and policy frameworks and legal consideration. Whatever we are doing some kind of planning process, it should have some policy frameworks as well. It should be legally, it should have some kind of strong things. So stakeholders involvement is a major thing to do any kind of activities in terms of water resources, and participatory approaches also required. So everything will be like a detailed project reports are crucial in terms of planning processes where we can get and we can exclude, we can include. Some of the environmental considerations in planning are environmental impact assessment EIA, environmental impact assessment, and environmental ecosystem preservation and biodiversity, and mitigation strategies for environmental degradation. So environmental impact assessment we can see, ecosystem preservation and biodiversity we can see, mitigation strategies for environmental degradation. So environmental considerations in planning, environmental impact assessment, ecosystems preservation and biodiversity. Functional requirements in multi-purpose projects like balancing irrigation, hydropower, and flood control. So we have to balance everything: irrigation, hydro control, hydropower, flood control, functioning requirements like, as I mentioned, irrigation, domestic, industries. So next one is trades-offs and synergies in multi-purpose design. So trade-offs and synergies in multi-purpose design and basin-wise planning, integrated water resources management, that is very important in terms of basin wise planning, and case studies for river basin organizations. So that means here we have to go with some kind of case studies. That means understanding rainfall runoff, understanding soil erosion, understanding sediment yield, understanding climate change. This all things need to be understood, and understanding groundwater potential zones. Like this, we have to understand each and every part of the watershed in a precise way. So, case studies of river basin organizations is important. Now, long term planning, climate change adaptation strategies. So, if you want to tackle climate change, so we need to be precise and we should know what are the strategies we are going. The best one is afforestation to reduce, to increase the infiltration, to reduce the runoff, and to reduce the temperature, and some kind of other strategies also need to be maintained. And coming to the other one is demand forecasting and sustainable allocation. So, demand forecasting means demand forecasting and sustainable allocation. So it should be in a sustainable allocation such that it won't affect the long term planning. So sustainable way we have to do everything such that it won't affect like climate change or anything. If you want to reduce this, we have to go with sustainable way. That means afforestation, the best example. Reservoir planning means, as I mentioned, in terms of water resource fund, site selection is crucial. Capacity determination in terms of sediment yield and soil erosion, and sediment control measures like check dams, gabion structures, and retaining walls, and non structural designs like LULC, land use land cover, things like increasing in afforestation. Afforestation is very important, and operations and maintenance strategies. So operation and maintenance strategies in reservoir planning. Now, concept of system engineering. A water resource system is a network of components like rivers, reservoirs, irrigation schemes, and users. That means it's a network. So, network of components like reservoir, rivers, reservoirs, irrigation schemes, and users, and combines civil engineering. That means it's not only related to the civil engineering, but also it should be taken from civil engineering, environmental, and economics. Economics means how much water is getting, how much we are going to distribute, and how much revenue we are going to generate, and what are the maintenance things. And computer modelings like SWAT model, HMS model, and this kind of things it is required, and decision sciences, and helps in understanding system behavior under different scenarios, like as I mentioned, climate change, land use, land cover changes. We can predict the land use, land cover changes. CA Markov model we can be used for future predictions. The benefits of system engineering. So holistic view of water systems, better resource allocation, resource utilization, adaptability to climate and demand changes, and facilitate sustainable development, and supports policy and planning with science-based tools. So these are the things. Now applications to real-time operations of existing systems. So real-time monitoring, that is sensors, adaptive management for reservoirs, floods, and control irrigations. And there will be some kind of case studies that we can see: extreme flood events and soil erosion. So some kind of sensors and remote sensing and artificial intelligence. So if you are able to use, then it will be helpful for understanding the watershed and for helpful for watershed management. So it will be adaptive management for like reservoirs, fault control, irrigation, and domestic purpose use, and many things. So studies, as I mentioned, case studies are most important. We need to do. We cannot study within one case study. We cannot give the report. So there will be multiple things are there: soil erosion, sediment yield. So soil erosion, sediment yield, LULC change, and rainfall runoff molding, groundwater potential zones. So these are the things required for this case studies, and more are there like future climate scenarios. So like that LULC also we can predict the future LULC maybe in 2025. If we are taking, we can take 2070. What is the future land use, land cover changes, CMRCO model. So these all things are the case studies individually. Extreme flood events, when it will be going to affect again, sediment is, soil erosion, and everything we can find. Individually we have to do, and combinedly we have to make a detailed report. And now we are going to revise it. First we were seen precipitation. So precipitation, types of precipitation, forms of precipitation, and went with the optimum number of rain gauges. And after that we went with missing rainfall data, and after missing rainfall data we have gone through. Next segment is After rainfall, we have seen immediate losses like transpiration and evapotranspiration. So transpiration, evapotranspiration, and interceptional. And another one is interceptional losses. So we have seen next step is after rainfall, we have seen losses and factors affecting individually and how it affects and what are the methods or measurements are required, and we have seen some kind of problems in evaporation. And after that we have gone through infiltration into the ground. So what is the infiltration into the ground? So we have seen Horton's infiltration. Before that we understood infiltration, percolation, groundwater table. So groundwater table. So infiltration we have seen, and we have solved some kind of problems called Horton's infiltration. And immediately we have seen first basic definition of infiltration, percolation, groundwater table we have seen. Then we went with Horton's infiltration. Then we have gone through phi index, W index, phi index, W index problems also we have seen. Next immediately we have gone through the component called runoff. In runoff, we have seen what is the runoff and factors affecting. So of the runoff per particular watershed, it may be shape of the basin, size of the basin, and it may be elevation, slope, and it may be drainage density, drainage texture, and everything will affect the soil erosion. So these all things we have seen in terms of runoff, and we have gone through that. And finally we have arrived with one more thing is called hydrographs. In hydrographs we have completely seen one component called hydrograph, that is discharge versus time. Discharge versus time. So before going to understand or solve this thing, we have went with triangular. Next we have went with a trapezoidal. Next after that we have went with the combination of the things. So we have gone through everything, triangular, trapezoidal, and a combination of the things, and we have derived some kinds of problems, and we have seen some kind of interlinked problems with respect to the phi index and W index with the hydrographs, and we have solved those kind of things, and we have solved maximum flood discharge with respect to the base flow and direct runoff and unit hydrographs. These all things we have seen in hydrographs. And finally, we have reached to one more topic, that is groundwater. Groundwater table, we have reached the finally one more thing, groundwater table. In the groundwater table, we have seen occurrence, that is occurrence distribution, and aquifers like as I mentioned, unconfined aquifer, confined aquifer. Unconfined aquifer, you can see it will be on the just below the surface of the or the atmosphere, the which whatever the groundwater table is there, that is considered as unconfined aquifer. Confined aquifer is it is between two impermeable layers, that is that one. And after that immediately we have seen wells, springs, and after that we have seen some kind of factors affecting the groundwater. Then we have solved it. We have seen some aquifer properties, sediment yield, porosity, and specific yield. So porosity means porosity will Sy plus Sr. So specific yield and specific retention with respect to porosity. So already we have seen the concept of the thing, if many particles are there, if gaps are there, that gaps are filled with water, that is called porous. And if that gaps are allowing to continue to flow water from top upper layer to bottom layer, that is called permeability. And permeability is solved with respect to Darcy's law. Okay, got it? Darcy's law. That is one of the property which is influenced and transmissibility. And another one is called this basic definitions. We have seen two kinds of problems in terms of volume lost from the groundwater, and we have seen the basic fundamental problems in that. And in hydrographs also, I forgot to tell you, S curve also we have seen some kind of things, and probability problems also we have seen, and everything we have covered entire hydrology subject. And coming to the final product, which we haven't discussed, is condensation. See, condensation is nothing but the water is escaped from evaporation and transpiration in gaseous stage with respect to vapor. Here, at one certain point, the water vapor, at certain point, the water vapor is converted to water drops in a specific a team in a specific area called clouds. So from there again it will be came back as rainfall. Again after rainfall we can see some kind of losses and runoff. Again it will be the thing. So this is called water cycle. As I mentioned in my first lecture, everything hydrology is depending on this one single image, water cycle. If we are able to understand each and every parameter, then we can do a sustainable watershed management of particular watershed. So precipitation is one of the major component, runoff is another one, infiltration, that is percolation, groundwater, and evaporation, transpiration, evapotranspiration, and condensation, and understanding the atmosphere, and understanding the soil natures, and land use, land cover patterns, and soil erosion, sedimentation, irrigation, reservoirs, is all collapsed together to make a sustainable watershed management. So now next we will see the hydrological models topics. That means in a simple sense, like as I told discussed before, that SWAT model. How SWAT model will work? Some input data is required, that temperature, precipitation, solar radiation, this kind of things. In a similar way, everything is required to make it in a better way. So here the soil erosion and sediment yield, or rainfall runoff models, or groundwater potential zones, or any kind of things, climate change, future climate scenarios, or land use, land cover prediction, everything will combine together to make a sustainable way. Now hydrological models we will discuss in the next topic. Here you can see. So rainfall runoff models we can see. So water cycle is also known as hydrological cycle. Hopefully now you people can understand what is what. So role of water in national development means just importance, that is agriculture, industries and domestic sector, and socio-economic impacts, and water security and scarcity. And coming to the point, water as a driver. Assessment of water resources, that is we have seen rainfall runoff models as surface water assessment, groundwater assessment, and data collection. And planning processes, we have seen stages of water resources planning, that may be pre-feasibility, feasibility, detailed project report, and stakeholders involvement and participatory approaches, and policy framework and legal considerations. Environmental considerations in planning, environment impact assessment, ecosystems preservations and biodiversity, mitigation strategies for environmental degradations, and functional requirement in multi-purpose projects like balancing irrigation, hydropower and flood controls, trade-offs and synergies in multi-purpose design, and basin-wise planning, integrated water resource management, and case studies of river basins organizations. And coming to the point, long-term planning, climate change adaptation strategies, demand forecasting, and sustainable allocation, and reservoir plannings like site selection, capacity determination, and sedimentation control, and operation and maintenance strategies. So, concept of systems engineering means network of the things, river, reservoirs, irrigation skips, and users. And it is a combined civil engineering, environmental economics, and computer modeling and decision science. Helps in understanding the system behavior under different scenarios, climate change, land use, land cover, land use changes, etc. And benefits of systems engineering approach, holistic view of water systems, better resource utilization, adaptability to climate change and demand changes, facilitates sustainable development, and supports policy and planning with science based tools. Real time operations means in terms of real time monitoring, adaptive managements for reservoirs, flood control, and irrigations. Some kind of case studies we have discussed: soil erosion, sediment yield, land use, land cover, and rainfall runoff models, and groundwater potential zones, and future climate scenarios which is going to affect that particular watershed. Finally, we have covered everything: precipitation, runoff, losses like evaporation, transpiration, evapotranspiration, and recharging, infiltration, percolation, groundwater, and coming back as base flow and condensation, and again water vapor to clouds, and again precipitation. So we have covered everything with respect to the water cycle, and we will discuss hydrological models in next one. So next topic in water resource engineering, we can see main types of hydrologic models. So hydrologic models are categorized into three broad groups. One is stochastic models, deterministic models, process description models. So before going into the hydrological models, like I would like to explain some kind of concept beyond that. So there is a RR model called rainfall runoff model. So for rainfall runoff model, for example, input is rainfall, output is runoff. So now input is rainfall, output is runoff. Now here we have to understand how it is going to predict. That means we will give some kind of data which is from field, and we will expect the same thing from software. That means here we have to see what is the input that these rainfall runoff models need to be satisfied with field data when compared to software data. That in technically we call it as actual discharge versus predicted discharge. So actual discharge is nothing but field, and predicted is software analysis. Like it may be stochastic models, deterministic model, process description models. Now hydrologic means like hydrological cycle means entire watershed basin. Now we have to be precise in terms of calculating. That means incorporation of land use, land cover, soil, slope, as well as some kind of rainfall, temperature, minimum temperature, maximum temperature, solar, wind, relative humidity, and other components. And we can make a future predictions also. So broadly classified into stochastic, deterministic, and process description models. Okay. Now each and everything we will see what is stochastic, deterministic, and process description. First one, stochastic models. So input is rainfall, output is runoff for rainfall runoff models. Got it? Now stochastic model is nothing but first point you can see. These incorporate randomness and uncertainty in the hydrologic processes. That means randomness. Randomness means there won't be any kind of the output whatever we are targeting, field data versus software, or else we can call it as actual discharge versus predicted discharge. So here when we are going with actual data but predicted, it will be having some randomness and uncertainty in the output data. That means that is what it is not successful method, and usually when the system behaves is not fully understood or inherently random. An example, it is used in time series. Like this different time series, different flood hydrographs we can see, but in a simple sense stochastic models, it is not it won't give accurate results at the end of the day. So that is the biggest drawback in stochastics models. Next one, what are the softwares or some kind of online platform which can be used for stochastic model or Studio, MATLAB, SPSS softwares. These three softwares we can be used for stochastic models. And next one, deterministic models. These use definite relationships and assumes no randomness. From stochastic models, we understood that randomness is there. Okay, and the same input always yields the same output. So whatever you are giving input, the same output it is expected. Same input means some kind of data. It may be temperature, temperature, and kind of LULC and soil maps and output data in terms of discharge of the field data and compared with the discharge of the predicted data. Further classified as spatial discrimination into lumped models. Here we can see three kinds of three similar watersheds are there. If I want to do some kind of analysis, okay. So what is the best model? What is the best assumptions we can make means there is no best model, there is no best assumptions. Each watershed will behave differently. In the same way, each watershed will accept different techniques. So we have to understand that each watershed is not similar, they are dissimilar. So someone may use X software for that particular region, it may or may not be fit for this region. So depending on the things. So now coming to the first one, lumped models. That means in lumped model, lumped itself defines summation. That means sum of models together. That means lumped model defines treat the entire watershed as a single unit and assumes uniform properties like rainfall, soil as a single unit. That means here some kind of input data I want to write rainfall, minimum temperature, maximum temperature, wind speed, relative humidity, and solar radiation. Or you can take LULC or soil or digital elevation model. See, basically, this all data when we are assigning to this same watershed, three times I have repeated. So if I want to take lumped model, so whatever the data you are giving here, input data. So this particular input data is considered for entire watershed. That means whatever you give rainfall, minimum temperature, maximum temperature, wind speed, relative humidity, solar radiation, or land use land cover, soil, DEM. So whatever the things, it will accept like entire basin will respond similarly. That means here it's the first line defines treat the entire watershed as single unit in terms of rainfall, soil, and everything. That's what defined. That means a lumped model means entire area it is defined as single unit. Whatever we are giving rainfall temperature, minimum temperature, maximum temperature, it will be considered as single unit. Now next one, semi-distributed models. So divide the watershed into smaller subunits or hydrological response units and some spatial variability. That means this is semi-distributed model. So entire watershed is divided into small hydrological units. Now you can see, for example, this can be treated as one hydrology, this can be treated as another one, this can be treated as one, and this entire area is treated as one more, and this can be treated as one. That means subwatershed 1, subwatershed 2, subwatershed 3, subwatershed 4, subwatershed 5. That means the entire basin, lumped you see, entire unit it has taken as a single point. Like a single, entirely it is considering as single. When it comes to the semi-distributed, it is not like that. It is divided into, first the watershed is divided into sub-watersheds. Then whatever the input data, we have to give it on based on sub-watersheds. So each sub-watershed will have rainfall, minimum temperature, maximum temperature, and wind speed, and relative humidity, and solar radiation. And other components like land use land cover, soil, and digital elevation model. Digital elevation model is for slope. This is the way semi-distributed model will work. Semi-distributed model will work with respect to sub-watersheds. Now coming to the final one, distributed model. So this example we will take as a distributed model. So distributed model means fully account for spatial variability in parameters like rainfall, land use and soil. Rainfall, land use and soil. High data and computational requirements. Now, what do you mean means initially lumped model means it is entire unit as considered as one unit. But coming to the point, semi-distributed means like in terms of subwatersheds, and distributed means in terms of grid. That means here you can see clearly. So this is grid 1, grid 2, grid 3, grid 4, grid 5, grid 6, grid 7, grid 8, grid 9, grid 10, like so on. Grid X up to X. That means distributed models will work with respect to gridded data, and the input data for this is same, but here the difference is grid 1, grid 2, grid 3. Each grid we have to provide rainfall, temperature data, and land use, land costs, like everything we have to provide in a precise way. That means you can see the development from lumped model, semi-distributed model, distributed model, you can understand. In lumped model, entire area is treated as one unit. But comes to semi-distributed model, you can see here entire area is divided into subwatersheds, and another one is simply it's for it is divided into gridded forms. Excuse me. And here lumped, semi-distributed, distributed, which is a good one, which is the best one. So here in some scenarios, like comparatively lumped is not or not at all good recommended, but semi-distributed and distributed are very good depending on the data availability, depending on the circumstances. Like we can go with respect to the things, like in terms of making the analysis. Now you can see lumped model means you can take the best example HMS, and semi-distributed strat and top model, and distributed model means example the softwares which are available are Mike. This will be done, this will be utilized. Now so now over to the process description models, last one. So empiricals relies on first one. So rely purely on observed data and statistical relationships, and no physical basis, and quick and easy but less transferable. That means here clearly stating just they are considering only the statistical data. You have to note it down. Purely there is no physical data means this can be used as machine learning, deep learning models we can incorporate. And conceptual model means represents hydrological processes using simplified concepts like water tanks and everything, and use calibrated and validated calibrated parameters. And physical models means uses physical laws First one is empirical, it won't use any kind of laws, but here it is using laws like law of conservation of mass, movement, and everything. Require detailed data and provides more accurate realistics. So this is a best example is SWAT model. So SWAT model is a best example and best suited model. How physical data, for example, rainfall, minimum temperature, maximum temperature, solar radiation, relative humidity, and wind speed. Other than this, some data we are giving to in SWAT model, that is LULC, soil, DEM. DEM is nothing but slope. So that means this SWAT is a mix of semi-distributed and physically based model. So SWAT is nothing but semi-distributed, physically based model. Got it? SWAT will use both techniques, semi-distributed as well as physically distributed model. So next, the hydrological models diagram you can understand in a simplified way. Please pause it and understand the flowchart. So hydrological models is categorized into mentioned previously stochastic model, deterministic model, process description. Okay, stochastic model is having some issues like randomness, and deterministic model again divided into lumped, semi-distributed, distributed. So as I mentioned, lumped model is it is treating entire unit as single. Entire unit as singles. Whereas in the semi-distributed, it will go with respect to the sub-watersheds. Whereas distributed, it will go with respect to the gridded. Now, process description, empirical, conceptual, physical. Now, as I told, there is a model called SWAT. It will incorporate both like semi-distributed as well as physical. Physical means LULC, soil, slope. That means semi-distributed sub-watersheds. That's what we will call it as semi-distributed physically based model. SWAT is called semi-distributed physically based model. So this SWAT model is used worldwide in more research areas. It's like most of the areas, SWAT model is used. So that is the one it can be understood. So now hydrologic models, that means input data requirements is calibration and validation. So applications like flood forecasting and flood assessment and water balance. So here calibration and validation in particular SWAT model, after giving the process to check how much extent it is working with respect to the observed discharge data, we have to go with SWAT curve. There we will do calibration and validation. In other words, training and testing. So both things we can do here. So training, testing is also known as calibration and validation. So more percentage of weightage is given to calibration and compared to validation. And applications, flood forecasting obviously, and drought assessment and water balance. Hydrological models are very much useful, and this data is useful for further groundwater potential zone, soil erosion, sediment yield, and other kind of things we can expect, like future climate scenarios, and these things we can see mostly. Here now we can come on quick types of hydrological models: stochastic, deterministic, process description. Again, stochastic means there will be a randomness and uncertainty in hydrological process, and used when the system behaves is not fully understood or inherently random. Example, time series. And stochastic models having or MATLAB SPSS. And deterministic models again divide into lumped, semi-distributed, and distributed. Lumped means treat the entire watershed as a single unit, assumes uniform properties. And semi-distributed means divide the watershed into small subunits or hydrological response units, and small spatial variability is considered. Distributed models means fully account for spatial variability in parameters like rainfall, land use, and soil. High data and computational requirements. Deterministic models means lumped models, HMS, semi-distributed models, SWAT, top model, and distributed models means MIXI. Coming to the process description models: empirical, conceptual, physical. Empirical models means there won't be any incorporation of physical data. So it is purely like it can be applicable for machine learning and deep learning approaches. And conceptual models, it will be like represents hydrological process using simplified concepts and use calibrated parameters. And physical models is like they are using the physical features like land use, land cover, soil, and slope. So these are the very important things, provide the most accurate and realistic things. Finally, approaching towards hydrological models, here classification has shown stochastic, deterministic, process description. So deterministic means lumped, semi-distributed, distributed models. So lumped means entire area is treated as one unit, semi-distributed means with respect to the subwatershed, deterministic with respect to the grid. Now process description means empirical, conceptual, physical. So physical means SWAT model, and semi-distributed means subwatersheds. So both like HRUs, hydrological response units. Now both can be combined and got some good results. That is SWAT. And input data requirements like calibration, validation, particularly when we are dealing with observed data and predicted data. If we want to match in a SWAT model, it is required to go with SWAT cup. That is calibration and validation. Calibration should be 60 to 70 percentage of the entire duration of the time, and validation. Applications are flood forecasting, drought assessment, and water balance. So this is the thing.